If you don't know your quantities, you don't know your project. Every construction project can be expressed as a series of quantities. That's meters of pipe, cubic meters of concrete, or linear meters of cable. Everything downstream that we actually care about falls out of these quantities. Our costs, our schedule, our payment claims, our subcontracts, our procurement, our material orders, all of these rely on having accurate quantities of work. A project where our quantities are wrong is a project where everything is wrong. This video is a complete guide to construction takeoffs. The process of taking a set of construction drawings and transferring these into an accurate bill of quantities. One of the single most important things we can do to ensure that our construction project is managed successfully. So in this video, we're going to be covering absolutely everything. Why takeoffs matter, what actually is a takeoff, where and what information we need to perform a takeoff, drawings, specifications, and the different types of construction documents and how to read them. Then we'll go into the actual takeoff process itself, the tools we need to do this before jumping into mechanical, civil, electrical, plumbing, structural, and all the specifics of the different types of takeoffs. Basically, we're covering absolutely everything you need to know about one of the most important construction project management skills. But to get started with, I really want to frame why quantities matter so much and why they are the foundation of every single construction project. And it's actually why the entire job of a construction quantity surveyor exists in the first place. So number one, we've got estimating. This is probably the easiest one to understand because when we think of a quantity takeoff, we think of it in the context of costing or estimating. And this is for the simple reason that our direct costs, the cost to do the physical construction works, are driven by the quantity of work multiplied by our cost per unit to do the work. For example, if we have to do 1,000 meters of trenching at $50 a meter, then it's going to cost $50,000. If we have to do 2,000 meters, it's going to cost $200,000. I just proved I can't do maths in my head while talking to the camera. It's actually going to cost $100,000. But at the end of the day, the relationship is simple. The quantity of work derives our direct costs, and the other important relationship to understand is that the quantity of work also drives how long the project takes, which drives our indirect costs. Which leads us on to the next relationship between quantities and other domains, which is simply the schedule. The duration of the works is the quantity of work we have to do divided by our production rate. If we have 1,200 meters cubed of concrete to pour, we can only pour 200 meters cubed per day. It will take us 6 days to do this. So our entire construction schedule is reliant on accurately understanding how much work we need to do. And as an extension to this, the entire construction methodology is going to be reliant on the volume of works as well. The way we do our trenching, it might make sense to use a specialist trenching machine if we have a huge quantity of trenching, but it might not make sense to do it if we only have short independent runs. Then we've also got our procurement, so ordering materials and letting subcontracts. Obviously, buy materials in the quantities that our takeoffs tell us. We order too little materials, we don't have enough materials to do the works, and our site stops. We order too much, and then we get excessive wastage and lose our margin. And on top of that, when we're actually letting subcontractors to suppliers, in all of our subcontracts, we will have a pricing schedule and a bill of quantities. And if these takeoffs are wrong, then our entire subcontract is wrong, and we'll get eaten alive with variations. And as an extension to our procurement, we've obviously got our contract administration. This is going to be both our upstream contract management and our downstream contract management. In our head contract, we'll have a bill of quantities, we'll have a pricing schedule, and then we've obviously needed to calculate this correctly during contract formation. And then we will only be able to claim against this. So our payment claim process will be reliant on how well we measure and prove the quantity of work we've actually done. And then when we're actually claiming variations to our clients, we need to prove when there's a change to direct costs that the volume of work has in fact changed. We can apply this exact same logic to our subcontracts, and without a quantity baseline, our contracts often are much more messy and difficult to manage. Our construction takeoffs will happen through every phase of the construction project lifecycle, from our feasibility stage when we only have basic concept designs through to our IFC and then actually through the contract process. At the start, when we only have basic concept designs and sketches, a lot of our takeoffs will be inferred or based on some simple heuristics or assembly-based takeoffs. For example, we might estimate the cost of the electrical works on a per meter squared basis, dependent on the type of building we're constructing. As the design progresses from concept design through to issue for construction, we'll have much more detailed drawings and schematics, and our quantity takeoffs will be a reflection of this. And then actually through construction, for every design change, every change to the drawings, we'll have to revalidate our quantity takeoffs and then determine whether we need to do variations. So basically, long story short, this whole introduction, I'm really trying to make two key points. Quantities matter a lot. And then quantities are universally applicable in all the different domains of construction management and across the entire life cycle of a construction project. So you don't just need to know quantity takeoffs. If you're an estimator, anybody in the construction industry needs to understand the basic process of how to read drawings, how to perform quantity takeoffs. Okay, next up, I want to dive into what actually is a quantity takeoff. Put simply, a quantity takeoff is simply the process we go through when we get a set of construction design drawings to accurately calculate our bill of quantities. Our bill of quantities is a complete library of all of our labor, plant, materials, and subcontracts needed to complete the project. You can think of it like our drawings show what we're building, our bill of quantities shows what we need to actually construct it. Now, some people use the terminology bill of quantities versus bill of materials interchangeably, but really a bill of quantities to me means that the bill of quantities contains our entire list of labor, plant, materials, and subcontracts, or we have our bill of materials, which is just a complete list of the materials. The, I guess, third category to this is often what you'll see as a pricing schedule, a schedule of values, which is just a summary of the key quantities used as a basis of contracts. So really, people use all three terms interchangeably, but they do mean slightly different things. So we've got our bill of quantities, which I would say is the complete list of labor, plant, materials, and subcontract costs needed to complete the project, which would basically be our direct cost estimate for the project. We then have our bill of materials, which is the entire list of the materials which we would use to order or do procurement. And then we also have what I would refer to as a schedule of values or pricing schedules, which is basically a list of the key quantities that is used as a basis of the contract. So schedule of values will be less detailed and specific. All right, the next thing to understand is the difference between a takeoff and an estimate. So a takeoff is simply a measurement of what's there. You might measure linear meters of drainage or the cubic meters of concrete in a slab. We would then apply an assembly to this to calculate the quantities of labor, plant, materials, and subcontracts. So for example, we apply an assembly of the quantity of concrete to a slab. So for example, this slab I've measured is 200 meters squared, and because of the depth, I can derive that it needs 20.92 meters cubed of concrete. Because I've got the area and I know it's got one layer of SL72 mesh, I can know that we've got 209 meters squared of mesh with some wastage, and we also need a vapor-proof membrane on the bottom of the slab. Basically, I've measured my primary quantity, which is a slab area. I've derived my bill of materials from this. I could obviously also include the labor to place the concrete, the labor to do the formwork, and so on and so forth. But this has no cost associated with it. It is an objective measurement of the quantities we need to perform the task. An estimate is where we take our bill of quantities and we apply cost information to it to actually calculate the cost of doing the work. So estimating is an extension of doing a takeoff. So takeoff is a key part of doing an estimate, but to do an estimate, we also need to allocate costs to all these. So we'd need to get quotes from suppliers to actually provide the concrete. We need to understand the scope of works to work out what our responsibilities are for disposing of the concrete. We'd need to factor in supervision and management. We'd have some indirect costs associated with that, like allowing for crib sheds and site facilities. All of this, I would say, is the act of estimating, when I would say the actual performing of the takeoff is purely the process of calculating the bill of quantities. The other sort of framework you could use is the takeoff is, I'm going to use the term relatively, but it's relatively objective in terms of how you actually build out the bill of quantities, because at the end of the day, you're measuring stuff. There is some subjectivity when we're talking about applying production rates to calculate labor, but I'll talk about all this later on. But then the estimate becomes much more subjective. So takeoff is really assembling the raw data. An estimate is applying costing and the business strategy to actually win the work. It's much more subjective. Okay, so now we've sort of framed the topic of what a takeoff is, why they matter. Let's give you some universal vocabulary. Now, the frustrating thing about construction is everybody likes to use different words to describe the exact same things. So I'm going to lay out my terminology. Your terminology might be different. Simply use these as replacements for whatever you want to talk about. But we have our drawings, which are the actual 2D plans that we measure. We have our specifications that describe the drawings and provide relevant information to them. So for example, we have a 2D plan of a concrete slab. Our specifications will give us more information as to the type of concrete, what sort of material testing we need to do, what sort of allowances there are for how high we can shoot it, what the process we have to vibrate it, what relevant standards it applies to. So specifications provide a lot more description. Now, again, because everyone in construction likes to do things differently, sometimes you'll have a drawing with a super detailed set of general notes and the actual specifications might not be as relevant, but in other construction projects, a lot of that information will live in the actual specifications, not in the general notes. I guess the thing to always be aware of here is that architects love to cover themselves by giving you way too much information. They love to repeat themselves. They love to always put in these catch-all clauses like saying the contractor is responsible for everything. Basically, with time and with experience, it's impossible to just learn in one video. You need to get a really good understanding of what specifications and what clauses actually matter, because there's always, when you look at construction documents, I find 95% of them are completely irrelevant, generic placeholder stuff. And then you have 5% of stuff that can meaningfully change how you do a takeoff, how it impacts your costs, your schedule, and all these elements. You have to be very clear on what the plans are actually showing you, where you would do your actual measurements and counting and volume calculations, but then also the underlying specifications that drive this. Then we have our takeoff. So I refer to a takeoff as the actual measurement itself. This can be the length, the area, the count, or the volume. So for example, on this drawing, our slab area, this would be our takeoff, which is the actual measurement of the 200 meters squared. Now, I know everyone is going to be asking about it, so I'm going to address it here, but can AI do quantity takeoffs? I probably get 20 to 30 questions about this a week. People are obsessed with the idea of AI quantity takeoff tools. I'm going to talk about this in a lot more detail later on and go into some reasons of where I think and where it doesn't work. But what I have been finding recently with Claude Code and Claude Cowork is you can actually get very good outcomes of using AI for quantity takeoffs, using a strategy of pre-processing PDF construction drawings and breaking them down into individual drawings and markdown files using a Claude Code workflow. If you do want access to that, I'll put a link to it in the video description of our AI community Contractor OS that's designed to help contractors implement AI in their construction business. And we also have some pre-built workflows in there, for example, breaking down construction drawings and also performing quantity takeoffs. So I'll put a link to that in the video description if you're interested in joining. All right. The next thing I want to talk about is, where does the actual information we use to perform takeoffs live? And that is going to be within construction drawings. So obviously, the core skill of performing a takeoff relies on us being able to read and understand construction drawings and extract from them the information we need to build our quantity takeoff. So in this section, I'm going to go into a fair bit of detail of how to actually read and understand construction drawings, basically to understand the structure of them, the different types of drawings, what they all show, and how to piece these all together. Because basically, at the end of the day, a drawing is a 2D compression of a physical construction project, which is always, obviously, it is a 3D. Now, I'm going to go through a couple of different sets of construction drawings. I'm going to go through a structural one. I'll show a plumbing and an architectural one, but really all the nuances about like the trade specific drawings, how to read electrical schematics and the specifics of what you would look at in a takeoff, I'm going to cover in the trade specific sections later on. So the first thing you want to understand is that while drawings often do seem like a pile of random information, they actually have a structured document hierarchy to them. And the different types of drawings need to be read in a way so you can understand how they all fit together. And basically the simplest framework to how to think about them is drawings start high level with sort of overall isometrics and plan views. And then they slowly, as you progress through the drawings, they add more and more detail. So you'll start to get into section views, detailed elevation views, and basically they add context. But really you always have this overall set of layout views or plan views. Again, it depends a lot on whether it's a services drawing where you might have that overall thing is more like a single line diagram and a schematic. But for things like concrete, structural, architectural one, you always have some sort of overall isometric or layout, and then you'll have detailed section views below it that add context to the drawings. So there's really 5 important types of construction drawings. We've got layouts or plan views. We have section views, we have schematics or symbol representations, which is much more common when we're talking about mechanical, electrical, and plumbing. We have general notes, and then there'll be some other typical things we need to pay attention to, like specifications and other supporting information, like, for example, architectural schedules. So when you open a set of construction drawings, the first thing you really want to look at is the overall plan view. A plan view is a top-down drawing. So for example, this is a warehouse. It has a cover page. The cover page is just a nice overall isometric so we can sort of understand what the project is. We have general notes, which I'll touch on a little bit more later, but basically these are more detailed that apply to the actual construction. Again, there's a lot of stuff in there that's probably redundant, but the most important drawing when we're talking about sort of architectural or structural, particularly even sort of plumbing and pipe layouts, is we want an overall plan view of the project. This is going to basically give us all the important information we need and show us where everything is. First thing we want to look at when we see a plan view is to understand what these grid lines mean. These grid lines will be referenced throughout the entire drawing set, and what they show is they're consistent across plan view, elevation views, and section views. So for example, this W1 grid line, if I go down to an elevation view of the building, or for example, this is another example of a more blown up close up. So this is probably a better example to use. But you see on this structure, there is a main office plan where they're saying refer office subplan on drawing S102. So this is S101. The drawing numbered S102 is the next one. And this is a blow up of this detailed office plan. And you can see this grid line W8, when it finally loads, is going to be referenced on this detailed office view. So if this makes sense, this is what actually helps you relate the drawing. So this, you see, is W9 grid line. This slab on this drawing is actually going a little bit. I didn't mean to highlight. This, I'll use the text a bit clearer. This close-up view is actually a little bit like that because we can see it goes from W8. So W8 is the edge of this slab. You can see that is that grid line. And then you can see the slab comes out just before W9, which is what is being shown here. So this is how we relate drawings to each other. And this is a useful concept to understand. And they're also going to be in longitudinal and latitudinal. Now, the next thing we obviously want to look at is we want to look for dimensions. Now, dimensions might be explicitly stated on the drawing, which there aren't actually any dimensions I can see on this drawing. But let's go down to this one, see if it's given us any dimensions. No, it hasn't. Does any drawing have a dimension on it? Let's go down a bit more. I mean, this drawing doesn't show a dimension, but you could just imagine maybe this said this is 12 meters. That is obviously a dimension, a horribly drawn dimension, but you will get dimensions laid out on drawings. The other way to get them is to understand that there is obviously a scale on this. So this drawing is 1 to 250, which means 1 centimeter you measure on the drawings is 250 centimeters in real life, or 2.5 meters. So if we wanted to, we could simply do a scaled measurement, which is 1 centimeter is 2.5 meters. Apply the scale and simply work out that this is 150,000 millimeters, or 150 meters, 157 meters, how everybody else on the earth would say it. So it's just basically they have a scale on them. You can read and interpret the scale. The next thing to understand are levels. So levels show the different heights of things, and typically, depending on where you are, they are referred to as heights above sea level or some standard point of zero. So what this means is this FFL stands for finished floor level. This has an FFL of 31.25. The top of the footing, so if you can imagine this is a slab which has footings below the slab, is 30.95. So from this, we can instantly see that the depth, the thickness of the actual slab is 130 millimeters, because the top of the footing is 31.25. So the top of the footing is 30.95. The finished floor level of the slab is 31.25. So you'll find on every drawing, they actually will call out heights. And what these mean is basically there's different annotations for them, but FFL will be finished floor level. Sometimes they'll just, for example, on earthworks drawings, they often just show the RL on them, which is, I actually don't know what it stands for, but I've never had to know what it stands for. I just know this means what the height is. Now, the next important thing to understand when looking at a plan view, and this is where we start to get into the other types of drawings, is you will see these little call outs. Now, there's none on this drawing that I can see, but there is one here. So what this means is this is what is referred to as a section view. So this means on drawing S711, there is a cut through of this slab where we can see this from this angle. So if I actually click on this, sometimes Bluebeam does this, sometimes it doesn't. I think it's how they set up the drawings, but this drawing actually doesn't let you do it. So I'll just go to drawing S711. And then on S711, so drawing S711, we can see there is this section view of the slab. So this is looking into the slab. We can see the depth. I mean, again, I don't know why this drawing has no dimensions. We'd have to scale that depth. But we can see that this is the cross section of the edge beam. So we've got the slab, we've got the cross section of the edge beam, and we can see how this interfaces with the wall. So we can see there's a slight concrete upstand, and then that ties into the precast concrete wall. So we go back. So you see that section view, that is looking into the corner of the slab. We go back to the drawing, we can see the actual cross section, which gives us insight to that structure. So we could use, for example, this drawing would give us the layout and the total area of the slab. Then we would go to the section view to get the exact depth of the actual edge beam. So a plan view drawing is going to show us where everything is, and our section views are going to show us the actual specific detail. So for another example, this is the footing layout drawing. You can see there's different, or I can't zoom in enough here, but you say footing type F7 or F6, we can see this is the section view of that footing. So this is the exact detail that it's a 600 deep footing that's 2100 by 2100, and that it has anchor bolts cast into it and 2 layers of mesh. We obviously can't get that from this drawing. The section views are the cut throughs where we get the actual detail from them. And again, you can see these grid lines coming up again to give us an orientation of where it is. Now, section views tend to be for close-ups of specific construction details. So you'll see them a lot in structural or architectural drawings, but elevation views are where you see an overall side view of the structure. Again, these grid lines come up. So WA, WB, WC, WC. So WA, if we go to the overall plan view, that is that point in the building. So this point refers to this grid line along here. WB refers to this point along here. And then we can get the elevation view to understand the drawings. The general notes are global notes that apply to all the drawings. If you think about this practically, how this would work, is say these footings always use 32 MPa concrete. The general notes would say all concrete is 32 MPa concrete, rather than every drawing that shows concrete putting a note that says this is 32 MPa concrete. So it's basically just a way of condensing everything down. Now, you may have these you sort of see 2 ways of people do it. You either have like supplementary specifications that detail all this information, or you have the actual construction drawings that show it in the general notes, or sometimes people do both. And it's why you always end up with this like massive mountain of information basically replicating the exact same thing. The other thing that you'll see a lot on general notes is actually, so you'll have obviously specifications, for example, all steel to AS 4100, but you often see responsibility clarifications, which is something you need to be careful with as well. For example, they'll say, the builder is to verify all dimensions on site. So this is, again, the way that architects try to pass through the responsibility to the contractor. Okay, so the next thing to pay attention to is if we have electrical drawings. And again, I'm going to cover all this stuff when we talk about electrical, plumbing, HVAC takeoffs, but you will have schematic drawings. So these are basically logical flows of, for example, power, water, gas, whatever. And they use symbols to reference different components. So for example, this is an electrical single line diagram. It shows a transformer, a 1000 kVA transformer of a certain voltage level, which is the incoming power supply. It flows down into the system where there's a current transformer and a circuit breaker. And then there is a separate 480 volt switchboard with a 1200 amp bus tie between them. So basically, this is rather than showing the actual, obviously rather than showing an actual schematic of a switchboard, this is just showing the overall system. When you're talking services as well, the actual layout drawings will show symbols to represent all of the different service components on the drawing. So you might have a certain symbol for a light fitting, for a switch, and the position of all these. Often you'll get a cable schedule or some sort of like pipe schedule that supplements this, but you may have to measure that yourself. It really depends what information they are giving you. My general rule would be that if the information is provided in the design package, you rely on that information. So for example, if they give you a cable schedule, I wouldn't create another cable schedule to cross-check that. I would rely on the cable schedule that's been issued by the client. The final thing worth mentioning is BIM. So BIM is just a much better way to represent the built environment than drawing is. When we think about a drawing, it's a 2D representation of something we're going to construct. There's always this level of abstraction behind it. BIM is just a much more efficient way to show where everything goes because it's a 3D view. So if you have a 3D model or representation of something, it is always going to be 1,000 times easier. I actually, having done a few commercial buildings or a few like sort of vertical construction projects, I struggle to understand how people built stuff before BIM. Drawings are just such a confusing way when we think about all these layers of section views and elevation views and orientations and having to flick through drawings, madly comparing information. BIM just simplifies that entire process. So if you have access to a BIM model, it is going to be 100 times easier. And the other thing is, because BIM, when you actually look at the data of an IFC file or some sort of Revit file, there is actually a structured database in there. So instead of actually having to count anything, BIM will just know how many light fittings there are. So BIM models almost make this entire process of construction takeoffs completely redundant. Okay, so we understand the drawings and the physical representation of the construction. I just very want to briefly talk about specifications. So basically, a drawing will show you what everything is, where it goes, but the specifications really add supplementary information to this. Again, a lot of this could be within the general notes, or it could be within a separate document referred to as a spec. So for example, on the architectural drawings, we might see a blockwork wall. On the specifications, we'll see the specific products that are required to do it. We'll see for example, the color, the exact type of blocks, the mortar we have to use, the reinforcement, the control joints, everything that's behind it. Specifications can be grouped into certain types, but again, coming from Australia where there's not a lot of consistency between how people do it, you may get an entire architectural specifications, or you might get a detailed specification for each of the individual products. In North America, for example, they use the CSI master format, which I think is a much better way to do it. In Australia, there is this NAT spec concept, but I've never actually seen it used in practice. In the UK, they have standard methods of measurements and standard specification structures, but again, it really depends where you are. CSI is probably the most widely used one, and I think it is a great approach to actually organizing construction data because there is a consistent approach to it. In Australia, really, from what I've seen, there's no consistent framework that's adopted broadly. Okay, so we understand where all this information lives and the different types of construction drawings we need to be looking at. Next, we need to talk about how to actually set up and perform a takeoff. This is going to be generic, and again, as I said, coming in the later sections, we're going to talk about the specific ways you do the concrete, steel, architectural, electrical takeoffs. So I think of this as a 3-step process. When you get a new set of construction drawings, step number 1 is to actually work out what you need to measure. What you need to measure becomes your list of takeoff items. Then you obviously go and measure it. And then, you can either do step 3 before step 2, it doesn't really matter. But then you would apply this to assembly. So for example, if I'm building a concrete slab, step number 1 would be to work out, I need to measure all of the concrete, steel reinforcement, and formwork. To get this, I need to measure the area of the slab and apply the depth in an assembly to get the volume of concrete and the quantity of steel mesh. I need to measure the perimeter to get the formwork, and I need to calculate the lengths of construction joints. The goal here is to simply measure everything required to build the project and then to break this down into combinations of different resources. The obvious part is that, different products require different takeoff items. For example, if we're installing cable tray, and I've got 300 millimeter cable tray, I've got 600 millimeter cable tray, obviously have to measure these two separately. I need to know the quantity of 600 millimeter cable tray, and I need to know the quantity of 300 millimeter cable tray. But What becomes less obvious is that if you're talking about building out the full bill of quantities and actually calculating the labor and plant associated with it, is certain we might have 600 millimeter cable tray that's mounted on the ground, and we might have 600 millimeter cable tray that is in a ceiling void. The cable tray in the ceiling void will have a different productivity and different plant requirements to the cable tray on the ground. So to actually accurately prepare our bill of quantities, we need to think about the different installation methods as well. For example, this might be with bulk earthworks as well. We might have different types of plants, or we might have trenching where it's the exact same type of trench, but in some areas of the project, there's more rock, and in other types, there's more clay. So we'll have different productivity rates. So the first step would be, before you actually start measuring anything, would be to go through the entire set of drawings and set up your takeoff structure. So the takeoff structure is going to be the list of items that you actually measure, plus their associated assembly below that. So you should always build this before you go and actually start measuring things. And you want to group it by trade, element, and then by the different variations behind it. So you might have an example hierarchy is you might have structures, below that you have concrete, below that you have slabs, and then you have the different slabs listed out below that. You might have a 32 MPa floor slab, 25 MPa blinding, a 32 MPa pad footing. So you've got different structures nested below that. Then once you have your entire list of items you're going to measure, you would then actually perform the measurements. And all measurements are really going to fall into three categories. We have area measurements, where we get the surface areas, floor areas, or wall areas. We have linear measurements, which is when we measure the lengths of trenches, cable tray, pipework, and fencing. And we have count measurements, where we do discrete counts of different items like piles, light fittings, and fixtures. Some people choose to include volume within this, but volume is really going to be just area times depth, and you derive it from an assembly. So I wouldn't include area, I wouldn't include volume in this typically, but really some people actually use the volume measurement tool. So when you actually look at a quantity takeoff software, you will have area measurements, linear measurements, and counts. Some people use this segment feature. I personally don't really use it, but like your area is obviously going to be the square meters. Your linear is going to be your takeoff items for lengths, and your counts is going to be counts. Very simple. And the other thing I would say is when you actually set your scale, it's simply going to be listed on the drawings, or you can calibrate the scale by using known distances between 2 points. So for example, if a drawing doesn't have a scale, but maybe this drawing is not a good example, but you know that measurement is 100 mil, you can use that. Well, actually it's listing the scale there, but you can use that length, that depth to get you could use those 2 points to calibrate your scale for that drawing. Okay, so we have those three main measurements types: area, linear, and counts. The next thing I want to talk about is this concept of a property. So when you measure area, you can also derive volume. So some takeoff tools will have you have your actual measurement, which might be flat area. But for example, you could have area with depth, which would give you the volume. So for example, if I go and measure, so delete this measurement, and I want to measure area with depth. Just quickly measure that. And because I've got area with depth, I can add the depth of this, which we say is 0.2 meters. And I can then get volume from this. Now, I could have done that with an assembly as well. I could have multiplied the area by 0.2 to get the depth, but you can also use these other properties. Where this, I don't think maybe the volume one I wouldn't use much. I would do that as I would typically do that more in an assembly-based structure, but you could do it with a property. The other way this is useful is, say the entire concrete slab is on an angle, or this is probably something more you'd use in earthworks. You can do sloped area, and so you measure the plane of the surface area, but you factor in the degrees of the slope, and it'll give you the actual sloped area, which is more important for the volume. And obviously, the true surface area is actually the sloped area, which is hard to measure on a plan view. When you're doing linear measurements, for example, linear measurements would be used for something like formwork of a slab because you're going to measure the linear on a plan view, but you're going to either apply to this either a property like linear with wall height, where you actually factor in that it's a 200 mil high slab, which is going to give you the surface area, or you can get sloped linear, again, if you're measuring a run of trenching and pipe work and it's actually a drain with some sort of fall in it, then to get the actual accurate length of the pipe, you would have a sloped with linear, or you might have some sort of hip valley linear where it goes down and then up. So it's just you can use these properties to basically convert what you would measure on the actual drawing to the true representation you're actually looking for. And then with count items, we have counts with diameter and depth, which would basically be, say we're counting piles, it'd be allow us to convert the actual counts we get into a volume. But again, you can use properties to do this by converting the measurement type, or you can actually do this with a assembly where you derive the secondary quantities from the primary measurement you take. Now, when you do your measurements, you always want to build these out into assembly. So for example, here I measured the edge beam, and from this I was deriving the volume of concrete, the length of the starter bars, the number of starter bars, and the different types of steel reinforcement. And to do this, you build out, for example, I knew this edge beam that goes around the edge of the slab, it was 300 millimeters deep and 600 millimeters wide. So to get the volume of concrete within the edge beam, I multiplied the 0.3 by 0.6, which converts the linear measurement into a volume measurement. Now, I'm going to talk in way more detail later on, so I'm not going to cover it here on the specific types of assemblies used for concrete, electrical, all the different trades. But basically, it's just this concept that you have the primary measurement which you take, which would be something like flat linear or area or counts, and you're using an assembly to derive your actual bill of materials that you need. For example, if you wanted to build an assembly for cable tray, you'd say for every 1 meter of cable tray you measure on the plan, you need 1 meter of tray material plus 10% wastage, rounded up to the nearest 3 meters because they come in 3 meter lengths, or you need 0.4 man hours of labor to install, 0.5 brackets because you need 1 bracket every 2 meters, and 0.33 splice plates because you need 1 plate every 3 meters. Or if I wanted to build an assembly for walls, say for example, we need for every linear meter of wall type 3, we need 12.5 blocks because that's how many counts when you do a 3 meter high wall. You need 3 meters squared of render because each linear meter at 3 meters high means 3 meters squared. Again, you need external paint, internal render, internal paint, reinforcement vertical bars, and deductions for openings. So you actually get huge benefits from this assembly-based process if you can create a library of different assemblies. So for example, every time I do a concrete measurement, I have this library of assemblies, a library for footings, doweling, slab on grade, structural fill, layouts, columns, walls. And below this, I have these pre-built assemblies. So for a wall, it'd be a linear measurement, and then all these are my derivative items from that. I can import this into my actual takeoffs, and then instead of from every project starting all my assemblies from scratch, I import them and I can reuse these templates across all my projects. And again, the final results when we actually do a library like this, following the assembly-based process, is we go to reports and we can have an entire bill of quantities based on our takeoff items. All right, now I want to talk briefly about takeoff tools, and I've already sort of showcased how and why you would need a takeoff tool, but I want to talk a little bit about sort of the progression, current 2D digital takeoff tools, BIM models, because I think that's very relevant to this topic, and also the future and AI quantity takeoffs. Again, something I know everybody is in love with. Well, I shouldn't say in love with the idea of. So takeoffs have obviously gone a long way. When we think how takeoffs used to be done, it used to be printing out a set of construction drawings, having a scaled ruler, a highlighter, a calculator, and some sort of notepad, and manually measuring every single length. Obviously, this is still done to some extent on small jobs where people want to print things out and quickly count them, but it's slow and error prone. And it's worth knowing how to do. It's not really that hard. It's basic. It's very, very simple. It's just laborious and time-taking. And people actually used to have offices like this where they were packed with people drafting, doing takeoffs, and all this stuff manual. It's obviously gone a long way from that. And now most people would use some sort of 2D takeoff tool. So I used to use a tool called Bluebeam, which is a PDF viewer sort of designed for construction, which it has more features than just takeoffs, but I find like the takeoff feature in this isn't really that useful. I use it for quick counts or just doing ad hoc measurements, but if you're doing a full bill of quantities for a project, it doesn't really have these features of being able to build assemblies or generate easy reports. Now, Bluebeam is highly customizable. I'm sure I'm going to annoy some people by saying that, and they're going to tell me, no, you can actually set it up to work in that exact same way. And that's great. I'm sure you can if you use Bluebeam in Excel, but I personally don't really use it like that. For my takeoffs, I use a tool called ZZ Takeoff, but again, there's a few of them out there. There's PlanSwift, there's another estimating software called Stack that all sort of operate in this similar way. You can easily do measurements and you can have this library of pre-built assemblies that you can derive your secondary quantities from. And it's very easy to sort of set up and store these libraries and reuse them as you want. So I'd say that is the main advantage of using a tool like this as opposed to using something like Bluebeam or a standard PDF reader. But again, like some people do really like Bluebeam. You can, for example, do like counts and measurements in Bluebeam, and then they get stored in your markup list. You can export your markup list to Excel, and you could have some Excel library of assemblies where you just copy in you just copy in your list of takeoffs, and then it derives your secondary quantities. You can definitely set up something like that in Bluebeam and Excel. I just personally think tools like this make it much easier and much more seamless. And if you're doing a lot of takeoffs, I mean, ZZ Takeoff is like $49 a month. It's obviously worth investing in something like this because it's just going to save you time and help you avoid making mistakes. Okay, AI takeoffs. Well, are they there yet? There are some AI takeoff tools that are boasting sort of accuracies of 95+%, but I believe the way they are measuring these scores, and again, I don't 100% know this, but I think the way they do it is on linear 2D takeoffs from plan views. The only part they are also automating is the actual physical counting themselves. So for example, there's Toggle AI, which is a really big one in the industry currently. And I mean, if it is something you're interested in doing, you can definitely book a demo and get them to show it. All of them will do free demonstrations. But basically, the idea is you upload your plans and AI automatically takes off and identifies all the different areas. There's another one, which is Civils AI, which again, basically does the same thing. You can upload your construction plans and then it will automatically mark up all the different areas. But again, definitely something, if you are interested, you can experiment and check these things out. You can get a free demonstration. But again, I think a lot of these tools probably overrepresent how much time it actually takes to do the physical counting. So much more of the time spent doing a takeoff. It's actually understanding the construction drawings and the scope. And that is something I think, or I at least am hesitant to automate because like even that example I gave before where you're talking about cable tray that's on the ground versus cable tray that's mounted in the ceiling. I don't believe these tools pick up things like that. That is only information you get from properly analyzing and understanding the construction drawings and spending the time to actually work out exactly what you're building, what quantities you need, and all the nuances around that quantities. Maybe in the future, there'll be this point in time where you can just pump your drawings and data into AI, and AI can pump out a complete bill of quantities broken down with all the plant requirements you'll need. But again, I don't currently believe it's there. And I think there's so much nuance around every particular construction project that I'm very hesitant to automate something like this. Okay, so far we have covered why quantity takeoffs matter, what is a quantity takeoff, how to do a quantity takeoff, the different tools you can use. Now we're going to move on to the trade-specific element of the video, where we're going to go through each of the individual trades like architectural, plumbing, HVAC, electrical, and we'll talk about the nuances of how to actually complete these quantity takeoffs. And for each of the specific trade elements I talk about, I've got a spreadsheet with a list of recommended assemblies you can use that there'll be a link to in the video description. You can spend all day counting every nut, bolt, and screw of a building and still be wrong. In this video, I'm going to show you exactly how to complete building and architectural quantity takeoffs using the assembly method. You can use this to quickly prepare a bill of quantities without sacrificing accuracy. Now, something that's tough about building and architectural quantity takeoffs is there are so many different drawings. You'll often see the same structure or wall from 3 or 4 different angles. So one of the actual challenges of doing a building takeoff is not double counting things. For example, if you see a bathroom, there will be a plan view of it, there will be a section view of it, there will be an elevation view of it, and they're all sort of showing the same thing. So you have to be careful with how you go through each of the different types of drawings and when to measure your quantities and when to reference the other drawings for supporting information. The basic framework is really quite simple. You have a primary quantity that you measure from the drawings. For example, this will be the linear meters of wall that I get from the plan view. You'll then come up with an assembly that you apply to your primary quantity. So an assembly, if you don't know what it is a ratio of a primary quantity you measure to a full bill of materials or secondary quantities. For example, this wall type, wall 3, for every linear meter of wall type 3 that I measure on the drawings on the plan view, I'll need 12.5 200 mil hollow blocks. I'll need 0.04 meters cubed of mortar. I'll need 4.5 kilograms of steel reinforcement. I'll need 0.012 meters cubed of grouts. I'll need 0.05 lintels for spacing. I'll need 4 wall ties, and I'll need 3 meters squared of external render and 3 meters squared of internal render. So as you can see, the only thing I'm actually measuring from the drawings is the linear meters of wall type 3, but I've actually built out this entire assembly with all of the ratios that sit below it. You can do this just for materials if you're doing this for, say, procurement, or you can include all your labor within this as well. So if you're doing this for procurement, you would just do materials, but if you're actually trying to prepare a full construction estimate, then you could also derive all your labor, plant, scaffold, whatever from this. So for example, for every linear meter of wall type 3, I need 0.6 hours of a block layer, I need 0.5 hours of a renderer, and I need 0.5 hours of a painter to paint each sides of the wall. So it's actually the only thing I measure from the drawings is the linear meters of wall type 3, and all these secondary quantities are derived from this. Now, you would complete, for a wall, you would complete this actual measure on the plan view. The only thing you would be referencing the section views for is to determine the height of the wall, which is how you're actually going to calculate your assembly. So from this elevation view, I can see wall type 3 is 3.851 meters high. So what I'm looking at in the drawings is I'm looking at these drawings through Bluebeam, but I find Bluebeam isn't great for quantity takeoff. So I use ZZ Takeoff for the actual takeoff and building out the library of assemblies. But really, you can use Plan Swift, whatever. There's a lot of tools that do very similar thing. The concept is really all the same, that you have some primary quantity you measure from the drawing and then a library of assemblies or secondary quantities that you derive from this. So I'm going to start by doing an example of walls, but I'll go through and do this for flooring, roofing, all the different types of architectural or building works. And so you can actually see an example of a takeoff sheet like this. I will put a link in the video description where you can get access to this spreadsheet for free. Okay, so for my wall 3 assembly, the first thing I need to know is what the wall is actually made up of. So the way you would typically find that is in the architectural specifications if it is not shown on the actual drawings itself. So for example, this is just an example set of drawings, so it doesn't really have a lot of information in it, but this is just saying it is a painting over a blockwork wall, for which is wall type 3. But typically you would have some sort of architectural specification that tells you this in a lot more detail. So for my wall type 3, because I went to the section views and I know it is about 3 meters high, it was actually 3.8, but I'm just keeping the math simple. I could then work out that for every linear meter of wall, how many 200 mil high blocks do I need within that? Say I calculate that at this 12.5. So every meter I measure on the plans, I need 12.5 blocks. I could then work out exactly how much mortar goes into this, and that could be for 40 linear meters of mortar at a certain thickness of mortar. I could measure that up for 1 meter and I could work out and then 0.04 meters cubed. Again, you get the point. It's simply understanding the wall 3 specification. So going into the architectural specifications and finding exactly what it is, what sort of finish does it have on it? Is it painted? All these things. And you go through and you calculate out all of these quantities. In my takeoff software, I'll create a new linear measurement. I've got to auto scale it. I'll call this W3 for wall type 3. And the first thing I'm going to do is add a material item, which is going to be the blocks, or we'll call these 200 mil hollow blocks. And I need 12.5 blocks per linear meter. I'm going to put this rounds up to the nearest 1, and then I am going to, the units is going to be each. So that is my blocks. The next one I need is the actual mortar itself, which again is going to be a material measurement. I'll call this mortar. And that is going to be for every linear meters, I need 0.4 meters cubed. Let's put 5% wastage on the mortar. And this is going to be meters cubed. Add another one, which will be the reinforcement that goes into the wall when they core fill it. That is going to be the linear meters of that times 4.5. So for every linear meter, I use 4.5 kilograms of steel reinforcement. Again, I'll put 5% wastage on this, and then I'm going to add the actual grout to fill the blocks. That's going to be the linear meters times 0.012 meters cubed. 5% wastage on the grout. I could add paint and everything else, but you're going to get the point, and it's just going to drag the video on. So I'm also going to add a labor measurement, which is going to be a total of 1.7 man hours per linear meter of wall. Call this labor, put that in man hours, and I will add a subcontract item, which is paint. So we're paying our painter per meter squared. This will just be times 3.8, which is the height, and that is going to be meters squared. So if I then go and measure this, again, I'll show you some different ways you can do openings later, but for now, I'm not going to worry about the actual openings in the wall. We'll deal with them later. And I realize that says wall type 1, but I'm just doing this as an example. So you can imagine if there's 105 meters, again, that says wall type 1. I realize that. I'm just doing this as a simple example. I need 1,317 blocks. I need 4.4 meters cubed of mortar. I need 500 kilograms of reinforcement. I need 1.4 meters cubed of grout. I need 180 man hours of labor, and I need 400 meters squared of paint. Say a painter is charging us like 25 bucks a square meter. That is why that paint is a subcontract item as meter squared. It honestly depends what your costs are and how you want to track these quantities. Now, in practice, when you have different wall types, you obviously have different assemblies, because wall type 1 is different to wall type 3. Again, I just did it as an oversimplification, but you should also put all of these in different colors and mark them all up so you can clearly see what you've measured and what you haven't. Now, you should do all your measurements on the actual plan views unless you have a really good reason to not be able to. Some drawings might be weird or specific or make it impossible to do this, but really you want to keep the plan views as your source of truth for all this information, because if you can't use the plan views and you start measuring stuff on the section views and the elevation views, it will get confusing very, very fast. Okay, so what about when you have gaps in the walls? So say, for example, this doorway or this space, if I go back to the actual section views, look at that wall type 3. Oh no, that's not the correct one. That's the roof structure. The facade. So say, for example, we have this door and these windows within the wall. So we're actually if we're using that method of just counting the linear meters and assuming it is the same height the entire way through, we're actually over counting these spaces. So there's a couple of different ways you can deal with this. When you actually go and count the door spacings, you can just put a note in there that you have for that area. For every door you count, you have a negative wall type 3 or something. Or for the window, every window you count, you can have a negative wall type associated with that. And that is just a placeholder for you to then, when you go to actually export your takeoff to Excel, you can then So I go to my report, you can see I've got a summary item of all of this. I could just have another measurement type, which is a negative takeoff item. So negative allowance for these spacings, which I then, when I go and do it in Excel, I just simply do that as a post-processing exercise. Or I could actually build this out as assembly. So in my wall assembly, I could have negative of all of these items. So I take away 4 blocks, I take away 4 meters cubed of grout, so on and so forth. There's lots of different ways you could do it, but all you have to do is make sure when you're actually counting the walls, the windows, the penetrations, that you're minusing those quantities from this. Again, I am sort of always of the view, and maybe this is because I cut too many corners, but I'm almost always of the view that you're better off being roughly correct than precisely wrong. Unless you have a wall like this, which is all windows, I am not too fussed if I slightly overcount a few of these things. So if I was doing this takeoff, I probably wouldn't even consider the doors as a double counting thing, because really you're including wastage, you're including all these other items. You could just choose to have a little bit less wastage. I think getting too precise with this stuff is you're almost going to have more errors and confuse yourself more. So I tend to not worry about that stuff unless you have a wall like this, which is literally all windows. So it wouldn't make sense to do a wall takeoff for that. All right. Next up is the floors. And again, this is not rocket science. Instead of counting linear meters, we're just going to be doing an area measurement. So let's call this F1 for floor type 1. It's going to be a flat area. And F1 is a floor hardener finishing. We've already covered the concrete works under concrete instructions. So I've done another video on concrete instructions takeoff. So I'm not going to redo it here, but let's assume this is after the concrete has been placed. We need to allow for the floor hardener, which is going to be our first material. So this is the application of this after the concrete, not the actual concrete itself. And the floor hardener, we need 4 kilograms per meter squared, which again, you could just get that from the product information. It'd tell you how much, that's not meter squared, that's kilograms. And we'll put 5% wastage on that. Again, the way we're sort of adding wastage to everything, and there's wastage in the materials. That's why I tend not to worry about the openings and things like that, because I sort of know all of these things are estimates. You can spend so long getting it from 90% accuracy to 100% accuracy, and you can spend all this time actually confusing yourself even more. So curing compound, we're going to measure that in meters squared. We can say maybe we've got a subcontract rate for polishing, and that is just going to be meters squared. And we've got labor for the actual finishing, and we're going to say that's 0.25 man hours per meter squared. That measurement's going to be like that. We do our start takeoff, and again, very, very complicated work here. We're just, why did it do that? I am just going to go and measure the overall area. Again, that's a bench, so we would have I'm being very precise and actually cutting out the wall. And then I don't think that really matters. But then we've got 821 meters squared, which is 3,450 kilograms of floor hardener, which seems like a lot. I'm not sure if that measurement, that ratio I had was correct, but again, it's too precise. So I'm just proving a concept, so I'm not too fussed about that. But yes, here we go. That gives us our areas, and we've derived our secondary quantities from that. Now, ceilings is where it can get a tiny bit confusing, and you just have to be aware of whether you're looking at the plan view of what is referred to as a reflected or RCP or reflected ceiling plan. So sometimes this for the actual, if you're doing like a plasterboard ceiling or some sort of internal soffit, then for those types of works, you would have to go to the reflected ceiling plan and consider and do that same takeoff, but on that drawing. Again, that's why with architectural takeoffs, they just give you so many different drawings and so many different angles from things. That's why it's careful to pay attention to the type of drawing you're using and what you're measuring. So the plan views is where you would get the floor plans, but if you have a reflected ceiling plan, which is basically like as the name suggests, it's like, if you can imagine, it's like a mirror looking up at the ceiling. So that is what you would get your quantities of plasterboard and things like that. Now, doors, again, doors and windows, you'd build an assembly of the actual door and window itself and the actual ceilings around that and all the components you need. And instead of those being a linear or an area, you simply count those, but the exact same concept as building up your assemblies. And for any sort of external facades or architectural work, again, if you have sloped roofs or things like that, that is where you have to pay a little bit of attention, and you might actually be better off using something like this sort of angle where you have a heavily sloped roof, or you can do this from a plan view, but you just have to make sure that you're factoring in the slope of the roof. So to do that, again, that's why I prefer using actual takeoff tools rather than things like Bluebeam. But you want to do that, you just go to create a new area measurement, and all these takeoff tools have this, and you simply do a sloped area and you enter in the pitch of the roof. So you will measure from the plan view, but it will factor in that the roof is on an angle. So again, it's the same concept as a floor measurement, but you just will need to do the sloped area. If you're trying to do this in something like Bluebeam, you can do it, but you just have to apply a little trigonometry. So obviously you'll use the height and the width, and then using Pythagoras' theorem, I think, if I can remember my year 8 maths, that will give you you measure the plan view, and then you have to multiply it by the ratio of the angle to the plan view, which you would get using Pythagoras' theorem. Okay, super basic, hope it helps, but this concept of assemblies and knowing what drawing you're measuring stuff off and keeping track of, basically, so do everything on the plan views, the RCPs for ceiling stuff, but if you're doing stuff on elevation views, you just have to be very clear when you're not using the plan views, so you're not double counting things. That's the biggest risk with architectural quantity takeoffs, and where you can confuse yourself, and building out these assemblies will save you a ton of time. Here's how to take a set of structural engineering drawings and turn them into a full bill of quantities. There's 3 very basic steps to this process: determining what to measure, measuring it, and then applying it to assemblies to convert our measurements to a bill of quantities. So in this video, I'm going to walk you through a full set of drawings, performing measurements for formwork, concrete, and steel reinforcement, and also put a link in the video description to an Excel template you can use with these different sorts of assemblies. So when we're doing a structural quantity takeoff, there's 3 things we're measuring. We're measuring the volume of concrete, we're measuring the meters squared, or if you're using imperial, the square feet of formwork, and the mass of steel reinforcement in kilograms or tons. So when you first open a set of construction drawings, there's generally 2 types of drawings you're looking at. You're looking at the plan views, which give you an overview, which is the drawing you're going to do all your takeoffs on. And then you'll have a series of section views that supplement and support this. Okay, so this concrete slab, I'm going to break down into a couple of different measurements. I'm going to obviously get the area of the slab, which is going to tell me the volume of concrete I need for the slab and the amount of SL72 mesh. Then I'm going to measure the perimeter of the slab, and I'm going to look at the section views to work out the depth of the perimeter, to work out my area of meters squared in formwork. Then I'm going to get the lengths of all these ground beams to get the quantity of steel reinforcement and concrete within the ground beams. Okay, so measurement 1 is going to be slab area, which is going to be measurement type flat area. And we're also going to get a volume from this. So I should just say the software I'm using for this is ZZ Takeoff, but all these quantity takeoff softwares are very similar. The principles are almost identical between whether you use Bluebeam, PlanSwift, or whatever. So the first material is going to be concrete, which is going to be the volume with 5% wastage. The second measurement we're going to get from this is SL72 mesh, which is going to be the area. Again, I'll put 5% wastage on that, and that unit is going to be meters squared. Then I'll start the takeoff, and again, very, very complex. I literally just measured the area, and that's going to say, based on that depth of 100 mil, you're getting 20.92 meters cubed concrete and 200 meters squared of steel mesh, because there's 5% wastage on that. Now, the next one I'm going to do is my perimeter formwork, which is going to be flat linear. But I also want to get what we'll refer to as the wall area. And I'll show you in a second, but I know the depth of the external formwork was 600 mil. So I'll just quickly measure this while I've got it open. So if you can imagine, we're pouring this entire thing at once. So I'm not measuring the formwork. Oh, what did you do, Tim? I just have to fix that up. So the reason I know that is 60 is because I went to the footing details, and if you see these typical EB1, which is the section view for the edge beam, you can see there's 300 mil depth on the slab. It has this return. There's a 100 mil slab we measured before. There's this 300 mil depth on the edge, and then another 300 mil from the edge beam. So if you can imagine, when we're actually constructing this, we'd pour the whole slab at once. We'd pour the slab and the ground beams. You'd perform a detailed excavation for the ground beams, and then excavate all the edge beams, but you would form up that full 600 mil at once. That's why I'm just measuring that entire slab. Okay, so the next thing we need to do is we need to do the quantity of concrete and steel reinforcement in our beams. So if we go to the section views, actually, I just noticed this poly membrane. So I'm going to add a new material. Give me 0.22 mil poly membrane. That's just going to be the area and meters squared. Okay, so what we're going to do now is I'm going to make this a little bit simpler. I'm just going to assume all the internal beams are an SF1 type beam and all the external beams are EB1. So EB1, we need the concrete, and so this is going to be a linear. Whoop, I don't want to do it on this one. It's going to be on this. EB1 is going to be a linear measurement, and it is going to consist of these 3 straight bars, which is going to be linear meters. There's a bar across that, but I'm not 100% sure if they've given us the detail on that. But we know the quantity of concrete is going to be 300 by 600, which is this full depth. Again, I'm simplifying it a tiny bit. So let's just say EB1 is a flat linear. And what do we have in there? We've got our material, which is the linear meters of concrete times 0.3 by the width by 0.6. We'll put 5% wastage in there. So that is going to be meters cubed, and given a name, which was 32 MPa concrete. Now we've got to do the steel reinforcement. So this is N10 600 spacing, those bent bars. We've got the mesh. So we're going to have N10 600 spacing for those bars, and we've got these direct bars. I'm assuming they're N10. So let's call this material. Oh, click the wrong thing. You could include labor in this as well if you want to start adding production rates. So N10 straight bars. And that is going to be the length times 3, because you can see these 3 bars going directly into the screen. 5%, and we're assuming you can buy them in 6 meter lengths, so it needs to round up to the nearest 6 meters. Linear meter is better because we've got that. Then we've got those short 300 cross pieces, which is, I'm assuming, are at 600 spacing, but I can't actually tell that from this. So we'll call that material N10. Let's just say we round these up to the nearest 0.3. And this is going to be the linear in meters divided by 0.6, because there's one of these every 600, 300 bars. So it's simple. And it's going to be the linear times 0.6. So you're putting one at every 600 mils. So that's going to be a count. Then we need these 3 N10 600 returns. N10 600 return. Oof, what did I just do? Ah, sorry. This is, I typed it over that. EV1. Edge beam. That is going to be, then these N10. So there's actually, we've got the starter bars. The linear length divided by 0.6. N10 starter bars. That's going to be divided by 0.6. Round up to the nearest 1. That's going to be a count. And then we'll call these the N10 returns. And again, they're every 0.6 because of the spacing. Round up to the nearest 1 because it's a count. Okay, so then I can simply, to be honest, I actually could have used the linear meters of formwork to do that. Probably would have been a bit smarter because it is actually the exact same measurement. Oh well, future lessons. So that is 60.85 meters. Again, almost exactly the same as the perimeter. There's 11.5 meters cubed of concrete in that. There's 192 linear meters, 3 times the length for those N10 straight bars. Those N10 300, there's 1 every 600 mils, so there's about 101, which that should round up to the nearest 1. There's 102 starter bars, so that gives us our edge formwork. Let's now do this for the SF1 ground beam. Let's just have a look at what's actually in that. So SF1 is just the 3 straight bars plus a starter bar. So was SF1. So flat linear. And that we're going to say, we're going to do the 32 MPa concrete is the linear times 0.3 times 0.3. Put 5% wastage on that. And then we want the material. N10 straight bars. That is going to be the linear times 3 because there's 3 bars going along there. Put 5% wastage, and that's going to be linear meters of bar. We want to round up to the nearest 6 because they come in 6 meter lengths. And then we've got material N10 starter bars, linear divided by 0.6 because we're assuming 0.6 spacing, round up to the nearest 1. Then I go to my SF1. And again, I'm assuming all these internal ones are SF1 because I think you sort of get the point of what I'm doing. And that gives us the quantity, 95 linear meters of that. We could also include the detailed excavation. Again, you can expand a lot on these assemblies, but that then gives us, if we then go to our report, we have now a full bill of materials. So we can go to group this by takeoff, or we can group it by item. Oh, I've slightly spelt those two concrete different, so it hasn't picked up the same, and somewhere else I've written concrete. And then I've spelt the bars in a few different ways, so it's not grouping them properly. But if we gave them all the exact same titles, you could see we've got a full bill of quantities for that slab. Okay, so the last thing I want to quickly talk about is how to do quantity of concrete and materials for different piles. So I'm going to start, when you're doing piling, this will be a count with we're going to do a circular count, and the other measurement we want to get is a volume measurement. If you think about this, if we say, you'd actually check this on the drawing. So we'll say the diameter of this pile is 900 mil, and the depth of the pile is 4 meters. Then we're going to have our concretes, which is we don't want the point count, we want the volume, the 5% wastage, and meters cubed. We'll imagine we'll get formatube for these as well. So formatube is like the casing for the pile. So we'll say formatube is the point count. It's going to be each. And then we'll call this, again, pile cages, because realistically, you don't steel fix piles, you buy cages. Look at that. And that takeoff. And again, piling is really easy. You just count the number of piles. And then it's giving us our concrete, our formatube, and our number of pile cages. So look, structural takeoffs really aren't that hard. You just have to really understand the basics of what these drawings are showing you, and then set up some very, very simple structures for how you go from the measurement you take on the drawings to how you derive the concrete, steel reinforcement, and formwork from that. In this video, I'm going to show you exactly how to take a set of civil construction drawings and turn them into a finished bill of quantities. There's 3 steps to this process: determining what to measure, measuring it, and then applying assemblies to turn our measurements into a full BOQ. So we're going to go step by step through each of the key civil construction activities and show you how to do this. So clearing and grubbing, bulk earthworks, drainage, channel and curbs, water reticulation, and landscaping. I'm not going to cover concrete, reinforcement, and structures because I'm going to do a structural quantity takeoff video covering that. The basic approach to any quantity takeoff, whether it's civil, electrical, mechanical, is that you have a set of primary quantities that you measure from the drawing. So these might be things like the meters cubed of bulk earthworks, the linear meters of trenching, or the meters squared of topsoil that we strip. You then apply these primary quantities you measure to assemblies. An assembly converts the primary quantities, such as the number of meters cubed of bulk earthworks, and then it applies this in ratios to a series of items to calculate the quantities of each. So for example, for every meter cubed of soil that I excavate, I need 0.02 hours of an excavator. We then have a set of ratios that we apply to our primary quantities to calculate our full BOQ. So for example, for every meter cubed bank volume of earthworks that I take out of the ground, I need to allow 0.25 meters cubed for the swelling factor. For every meter cubed bank volume that I excavate, I need 0.02 hours of an excavator to do this. This is based on a production rate of 50 meters cubed per hour on the bank volume. I might need a dozer for 0.01 hours to spread it, but depending on the haul distance, I might need 0.025 hours of a dump truck. Or for example, for every linear meter of stormwater pipe on the drawings, I need 1 linear meter of pipe. I need a gasket every 2.4 meters of pipe length. I need bedding excavation based on the cross section of the trench. So basically what we're doing is we have our primary quantity, and then we have a set of secondary quantities that we calculate from the primary quantity we measure on the drawings. Now, this spreadsheet with this library of assemblies, I'm going to go through some simple examples when I actually do the takeoff. I'll put a link to in the video description so you can download it for free. So generally the first step in any quantity takeoff is you'll simply go through the drawings to get a comprehensive understanding of what you would actually be measuring. So within the drawings, you'll generally have some site overview plan, which has all of your key information on where you'll actually be doing the measurements. And then to supplement this, you'll have a series of section views or detailed cross sections where you can look close up at the detail to work out things like depths or specific sections. So I'll give you a very simple example. If I look at this overall site plan, and this is a commercial construction project showing a series of new buildings, I can see that this building, if I refer to the section view of it, it'll show me that on the plan view, I've got my finished floor level, and on my section view, I can see the depth of the excavation. So using these two bits of information together, I would be able to calculate the volume of bulk earthworks. Now, so the first step of any quantity takeoff would be to go through and actually just create a list of every individual item that we're going to measure. I'm going to do this in stages so it makes a bit more sense and talk a bit more detail about each of the specific items like drainage, bulk earthworks. But the first step would be going through a whole set of drawings and creating your list of items to measure. Typically, you would need some supplemental information to understand this in more detail. So this is just a simple set of plans. It's not even an issue for construction. But in addition to this, we'd look at things like the geotech report to understand different soil types, bearing capacity, the water table depth to determine if we're going to have to do any dewatering, whether the material is suitable to reuse, which is going to impact the imported fill volume, and any bulking or swelling factors for different types of materials. If you don't understand the terms bulking and swelling, bulking pretty much means that when you excavate material, so the material in the ground is compacted, when you pull it out of the ground, it swells. So the volume we measure on the drawings would typically is the actual in-ground, what is referred to as the bank material. When we excavate that, it swells. So if we're measuring the number of truck movements we need, that would be the bulked. We'd have to add a bulking factor in that to account for the additional volume in the trucks. But then when we're importing material, we have to factor in the opposite impact of what's happening to the soil because we'd be compacting that again. So the actual volume we need to compact in the ground is going to be less than the volume of soil that we need to import total. We might have supplementary specifications which say what type of material we need to import, where specifically we need to buy that material from, and if we're factoring in erosion and sediment control, those quantities typically wouldn't be on the civil design, but we'd have to refer to a separate set of drawings. Okay, so the first quantity I'm going to be measuring is the clearing and grubbing quantities. You can imagine we start with a clean construction site. There's grass, there's topsoil, and the first thing we have to do is we have to remove all that to begin our construction works. There's really two quantities you want to measure when you're working out clearing and grubbing volumes. Number one is the total surface area of the site footprint. So this is going to be a measure in meters squared. Actually, I just want to quickly say something I should have mentioned before is I'm doing this takeoff in a software called ZZ Takeoff, but the actual underlying principles are exactly the same no matter whether you're using PlanSwift, Bluebeam, or even Adobe and just an Excel spreadsheet. So all the principles I'm talking about are universally applicable. This is just the specific tool that I'm using. Okay, so what we need to measure when we're working out site clearing and grubbing is we want to get the total meters squared, or again, I use metric, but you'll just have to replace my metric measurement with my imperial one. But the first thing we're going to measure is the total square meters of the site and the number of sort of trees and physical objects we have to remove. So for example, typically when you get a site plan, there'll be bushes you have to remove. Those will have an increased cost associated with them. You might have to get a subcontractor to chop down the trees than you would for typically just using site clearing, which is using something like an excavator to just strip the topsoil. Okay, so topsoil strip is going to be an area measurement. I'll call this clearing and grubbing. It's a flat area and we're going to measure it in meters squared. Now, in terms of the materials and labor we need to do this, we need an excavator. The formula is going to be the area in meters squared multiplied by our production rate. So a reasonable production rate for topsoil stripping with a 20-ton excavator would probably be around 25 meters cubed per hour. Now, in this video, I don't want to talk about how to come up with these specific production rates because I've done lots of videos and content on estimating on how you actually build your own production rate libraries. So this isn't so much about the actual number, but it's more about the methodology. So if I say we've got area in meters squared, we want to multiply that by the depth. So we're going to say we're going to do a 200, we'll actually say 150 mil topsoil strip multiplied by, so if we go area meters squared multiplied by the depth, that gives us the volume multiplied, well, it wouldn't be multiplied by our production rate. It would be the ratio of the production rate because we want to convert an area to hours. So we should divide by the production rate, which is 25 meters cubed per hour, which will give us, should just open that up. That'll give us the number of hours we need an excavator for to do the topsoil strip. The other thing is we need a to to remove the topsoil from site. So we need that same formula, which will give us our volume, divided by a reasonable production rate for moving topsoil. So we'll say 30 meters cubed an hour, and we'll allow 10% wastage on this. And that is going to be truck hours. And then the final thing is we'll have a subcontractor cost, which is offsite disposal. And we're going to get charged per meters cubed for that. So to 0.15, which just gives us the volume, because this is the units for this is going to be meters cubed. And again, we'll allow 10% wastage. So we've got our takeoff item. Going to click start takeoff, and then very, very simple. I'm just going to measure the entire footprint of the site that we would strip. So when we're talking about topsoil stripping, you're not going to strip exactly up to the edge of your works. You're likely going to strip like a tiny bit more. But because I've already got wastage in my measurements, now I'm just going to start measuring with a little bit of an extra footprint around. Again, this is a bit conservative, but it shouldn't make a massive difference. Actually, this is a bank, so that bank would form part of the overall works. Again, something like topsoil stripping, you don't really have to be incredibly precise. It's more about just being realistic about the footprints of the works and what you would actually strip. We're not going to strip that because that's an existing building. And there we go. That was 17,000 meters squared, which is going to take an excavator about 100 hours, 90 hours to remove all the truck. And again, when you're actually going and putting this into an estimate, you would round up these numbers. So I would refer to that as an estimating task. When we're talking about your actual bill of quantities, I would always use the actual production rates. And then the estimating task is balancing all these numbers. And then we've got 2,800 meters cubed to dispose of, which if you think about it, that is 17,000 meters squared multiplied by that depth of 0.15. The other thing, as I said, is I would go, if you actually have to chop down trees, I would go and use a count measurement to count the number of trees. But in this footprint, there aren't any trees that we're chopping down. Okay, so my drawing does not get too messy. I'm going to turn off that layer, and now I'm going to go and calculate my bulk earthworks. So I've got a little bit more real estate. I'm going to close that. So measure bulk earthworks, we want our total cut and fill volume. The way we work this out is we have our contour lines, which are the existing height of the existing height currently. We've got our drawings, which show the finished floor level at different spots. So we can say this is 1252 FFL. If we go down here, where are some other heights? That's 1251, 1251, and 1251. So if we think about this practice, when we have stripped the topsoil, we've stripped 150 mil. So we have dropped the overall site level by 150 mil. If we go to our topsoil, and again, you'd have to look at this more specifically, looking at every individual building if structures have different depths, but honestly, I can't really, for the purpose of this video, it's too detailed. The concept is exactly the same. Then we can look at this slab and the depth that we have to excavate to for this slab. Again, these footings I would refer to as detailed excavation, and I'll talk about how to measure those volumes separately. But in terms of the actual overall site cut, this is going to be based on the finished floor level minus that 150 mil we stripped, minus the thickness of the slab. So basically what this note is saying is if from our finished floor level, which is we'll call 125.2, bring up an Excel to show the workings for this. So FFL is 125.2, and I know it varied slightly, but again, I'm trying to make this as simple as possible. We've got thickness of slab, which was 125. If I go back and look at this cross section, then this is saying to top 150 mil of bulk earthworks platform to be ripped, sacrificed, and recompacted. And then the other 150 mil below that, I'm assuming we would just compact. So let's be top the removal. Let's say we're going to remove 300 for those 2 layers and assume we're going to replace and compact the entire thing. So it's top 300 removal. Cut depth. So what we need to get the overall site to is 827. So we're pulling out 450 mil of material across the entire site. And then through our site, we then need to compare this to what the existing levels in the site are. So you can see this contour line is at 1252. Again, matches our finished floor level. This is 1251. So this area is 1251. And then this area is 1250. So we've really got 3 different depths we're going to have to excavate depending on the existing level. There's going to be this area, which we're going to take the average of the 2 contour lines. There's going to be this area. We'll take the average between 1251 and 1250. And then we'll take this area, which will be the average between 1252 and 1251. Okay, let's call this cut volume. And at the, when existing is 1252, our cut is going to be, meant to bold that. Our cut is going to be, so when the existing is 1252, actually to make it a bit simpler, we'll be a bit more conservative and we'll just assume the high level of the contour for this area. So again, typically you would have more detailed drawings, which would make this easier. But our cut is going to be 1252 minus this, minus what we have already excavated, which is 150 for the topsoil strip. So we're going to have a 275 mil cut there when it's 1251 and 1250. We're going to have that minus 150. And then that minus 150. Now, that was probably a stupid analysis to do because the difference in height from here to here is 1 millimeter. So I can probably be relatively conservative and just use the same measurement for the entire thing. Again, that was probably a stupid analysis to do. My brain wasn't really working. But overall, the cut, we'll say we've got a 275 mil cut. So we're going to go new area. We'll call this earthworks cut. The measurement is going to be flat area with depth. The depth is going to be 275. And then across this, take this, a look at my assemblies to just build these correctly. I'm going to have equipment, an excavator, an area. It's going to be the area meters squared, but we don't want the area. We want the volume divided by our production, which is going to be, because we're bulk removing, it's going to be much faster. So it's probably be about 50. The units are going to be hours. Again, I mean, I'm just going to make it simple and assume these are wet hire. Truck. And again, actually, something I should bring up when we do this is this just earthworks cut to depositing on site. So it's not, we're not assuming we're going to take it away, because if we actually look at those section views, most of that material, except the topsoil that we've already stripped, which roughly matches the depth of the slab, is going to be recompacted on site. Because if we look at that section view, that top 125 mil slab, that is roughly what we excavated when we did the topsoil stripping. These 2 layers, we're actually recompacting. My measurement went away. Okay, I'm going to start this again. Cut volume, flat area. We want the volume we're excavating 275 and we want, say, an excavator. We want to measure the volume. I'll delete that. And the hours are going to be that. Oh, sorry. The volume divided by 50, which is our production rate. And let's just match that to a truck. We want the volume. And again, super, super simple. It is going to be so if there was big differences in heights between these points, and there's not on this set of drawings, the way you would do this, you would measure between the contour lines and work out the different depths for the different contours. But because there was almost no difference between the measurements, I am almost going to do, actually remember, this is just the cut volume, so I don't need to over measure. I'm just, so this is going to be my entire footprint for the building that I'm excavating. To be honest, these trench drains, you probably wouldn't actually do as part of the bench. You'd do them as part of like a detailed excavation task. I shouldn't really be measuring those, but already started. So this is, and again, a lot of these slabs, if I looked at the section views properly, which would have been, again, like a bit too detailed for what I'm trying to achieve with this video, you'd probably find that some of these different slabs had different depths. So you wouldn't do like a bulk excavation the way I'm doing it. You'd look at each individual slab and what the depth was. So that was 3 million meters cubed. Let's think about that in practice. My formula was missing a decimal place. And that has dropped to 3,000 meters cubed, which sounds a bit more realistic. 50 meters cubed an hour gives you 60 hours with an excavator, and I obviously didn't divide by 50 on this, which makes more sense. Now, if you wanted to work out, say, for this example, we're reusing materials. So truck movements, if you're doing on 50 meters cubed an hour, what I probably didn't show there is because when you rip out the soil, it would loosen, that your truck volume would probably, if your actual truck production rate was 50 meters cubed an hour, you would want to times by 1.1, which would be the swell factor for moving the material. And then if you wanted to work out, I won't go through and do the fill volume, but if I wanted to do the fill volume, what I would do is I would take what the imported fill is and divide it by the compaction factor, so that volume we're importing would be higher than what volume we actually need to put in the ground. Now, something I want to touch on when you're actually doing cut to fill volumes is when you looked at the example from this drawing, we could see we're pulling out 300 mil. Now, because when you look at, say for example, our cut is 1,000 meters cubed, our swell factor is 1.1. So that would be, the swell factor is how we would do the actual truck movements offsite, would be 1,100 meters cubed. But say that volume we excavated, that 1,000 meters cubed, say we need to import material, say we're importing new fill, the amount we have to import would be, let's call it the import volume, might have a different factor if it's a different materials. So that's 1,000, might actually be 1.15 that we have to import. So it might be 1,000 meters cubed we have to import. then this would be the volume we need to compact as well. So it's just important to understand for different materials, the cut and swell volumes. And it's also important, should just realize that I was covering myself with my, when I was doing those calculations, which is embarrassing, but whatever. So you can see there's a difference in these cut and fill volumes. And that's why it's important to look at the geotechnical report to both see, one, whether you can actually import and reuse material or whether you have to take it off site. Second element of this is what the swell and bank volumes will be, because different materials will have different volumes that they swell and bank. So you can just Google these to find out roughly what they are. And this is actually quite a good diagram. So you have your bank, which is what's on the earth, your loose, which is what you place before you compact, and then your compacted volume. And then there'll be typical ratios for different materials, but I can't see them here. Here we go. You can see clay will have a higher bulk or swell factor than something like granite, which makes sense because it wouldn't really compact. But basically, depending on the actual type of material you're removing or compacting, this is where you could simply Google these rates or the standard tables you can look up. Okay, so earthworks is probably the most technically complicated thing you have to measure, because you do have to think about these different factors. But if I turn off those two layers now, what I want to show you a quick example of now is measuring drainage, measuring quantities of drainage and subsurface trenching. Again, this is much simpler to measure. But say, for example, we want to know our BOQ for this 160 mil PVC pipe with a 1 in 64. This is going to be a linear measurement. We'll call this PVC pipe. And the measurement type we want is sloped linear, and we'll say degrees. Again, this is probably a bit overly specific, but if we think about that is a 1 in 64 called grade. Actually, degrees. And that is approximately 1% on a linear measurement. And the material we're going to need for that is obviously going to be, say, PVC pipe. It's just going to be the same as a linear length. We'll say we've got a 5% wastage measure. We'll say we can only buy the pipe in, say, 6 meter lengths. So we need the quantity to round up to the nearest 6 meter. I'm going to say that is 6 meter lengths. We're going to have, let's say, an excavator. An excavator that can do the linear length divided by 10, because they can trench 10 meters per hour. And then we're going to need, say, maybe we need sand to backfill. We'll say material. We'll say sand. It's going to be the linear times, say the trench is 500 mil, say 300 mil wide and 700 mil deep. We'll say give it a 5% wastage factor, and that's going to be meters cubed of sand. Again, there's more things you would need to do in practice. And then I'm just going to measure. Click on that. And that is my linear meters of drainage with that 1 degree grade. And you can see, because I can only buy the pipe in 6 meter length, it's rounded up to the nearest 6 meters. I need 5 hours at roughly 10 meters per hour to trench that. And then I need 10.7 meters cubed of sand. Then for the manholes, that is going to be a count. Let's call these manholes. It's going to be a point count. We'll need the actual manholes each. That's really easy. That's just going to be the count. And let's just say we need, again, we'll say an excavator, and it's going to take them 4 hours per pit. Hours, start takeoff, and I'm just going to go 1, 2, 3. Very, counts are very easy. Okay, the next one I want to show you is how I would do detailed excavation. So if you look at these section views of the foundations of a building, let's say at each corner, and you'd have to compare the layout to this. So if we look at the layout of the building, we can see that there's these footings. Now, realistically, you could either excavate the individual footing, or if they're close enough together, which you could just excavate the whole trench. But let's just say this is the foundation layout. This is how I would calculate the volume of excavation to do that. So say, let's go back to our site plan. Let's go to that relevant building, the classroom, and we know that, let's say there's a footing at each of these corners. I know from that layout, it wasn't similar to that. So detailed excavation, I would do using a count. Let's say footings. We'll use a square. It's going to be a point count. And we're going to need, let's just say, no material. An excavator. It's going to take them 2 hours to excavate every footing. And we need to, say, equipment, a truck. And we're going to use that same productivity rate for the truck, because we assume that the truck will be sitting there while the excavator fills it. And then you could just count. So there's one footing at each corner. You could just count the number of individual footings. And in the same way we did the trenching before is how I would factor in the detailed excavation of any of these concrete drains. You just measure the lineal meters divided by the production rate. Now, curb, again, super simple to measure. Curb, so all this above ground work is going to be curb. And let's just say we're getting a subcontractor on a per meter rate to install curb. We'll call it curbing subcontractor. And it's just going to be the lineal meters of curb. And it's just a flat linear. So all this is you'll see pretty quickly that all these different measurements are really going to be area, linear, or count. It's not the most complicated concept in the world. So you'd go through, measure all the curbing distances. I'm sure you get the point. Then for paving, so say this is a type A 80 mil paving. We want to get the area of that. Type A paving. Assume we're going to get paving subcontractor. It's going to be meters squared. And again, sorry, I'm going to click on that. And again, very, very sophisticated. I'm just going through and quickly doing the measurements. Now, one thing I'll just stress is that this stuff is really easy. Probably the biggest mistake you'll make is not measuring the right stuff. It's not actually doing the measurements where you stuff up. It's actually going through and working out everything you want to measure. So I've done this video a little bit in the wrong order because I wanted to go through and talk about each concept. But in practice, what you would do is you'd go through first and define the list of everything you need to measure, which is going to be a function of what's on the drawings and what your how you're going to deliver the work. For example, the cut volume, the fill volume, that depends on whether you can reuse material, whether you measure paving like this as just a subcontract rate, or whether you need to get a full BOQ of each of those individual materials. It really depends how you're delivering the work. Here's a step-by-step guide to plumbing quantity takeoffs. In this video, I'll show you exactly how to take a set of construction drawings like this and to quickly turn them into a complete bill of materials using the assembly method. So there's going to be 3 steps to this process. First, we're going to understand the different systems and what is actually shown on the drawings. Then we're going to build a library of assemblies from which we can then measure items on the drawings and then derive a full bill of materials. And then finally, the easiest part is we're going to actually go through and measure what's shown on the plans. And I'll put a link in the video description to a plumbing quantity takeoff spreadsheet you can use and a library of assemblies that you can go from taking your primary quantities like the length of pipe or the number of fittings and basins and how to derive a full bill of quantities from this. Okay, so first I want to start by actually explaining plumbing systems, because if you don't understand this part, it's impossible to read and understand and interpret the drawings and then derive the bill of quantities. If you do have some experience with plumbing, then feel free to skip this part because it's probably going to be a little basic. But when we're talking about plumbing systems, we're talking about 5 separate subsystems. We've got cold drinking water or cold water supply. We have our hot water supply. We have sanitary drainage, sometimes referred to as wastewater. We have stormwater drainage, which we refer to as our rainwater system. And then sometimes we'll have a wet fire protection system, which is the sprinklers, hydrants, and the hoses and reels. Now, most of these systems we can either break down into sort of 2 key items. We've got the actual fixtures and units. For example, with a cold water supply system, we'll have taps and valves and units that we will count from the drawings. And then we will have pipe work that reticulates and distributes this that we will measure the lineal meters of. Doesn't really get much more complicated than that. But to really understand what we're measuring, we first sort of need to understand these different systems. So cold water supply is how you get water from the utility provider in the streets and distribute it to all of the taps, toilets, showers within the building. So on low-rise buildings or small commercial buildings, this will be at the water main pressure, but on high-rise buildings, we might have some sort of pump system to increase the pressure and to get the water to the top of the buildings. We can have different types of pipe. We can have copper pipe, PVC pipe, or different materials. And often there will be some sort of utility main connection, and there will be some sort of backflow prevention device which prevents water from your building or your facility flowing into the mains water supply. Now, because none of us like having a shower when it's cold, we will also have our hot water supply, which is basically we take the cold water supply and we add a water heater to it, and then we have separate pipework that runs through the building and distributes hot water where it's required so we can have a warm shower. Sometimes you will have tankless hot water systems, which are instantaneous boilers at the actual point where you use the hot water. And for larger buildings, we may have a recirculation pump so you don't have hot water sitting in the pipes for ages and getting cold. Next up, we have sanitary drainage. So this is when you flush your toilet, the water goes down the sink. You have non-pressurized pipework that drains through gravity back into the sewage system in the street. So also you will have vent pipes that run through to the roof, which prevents your odorous or smelly water or smelly air that sits in these pipes running back up and the smell coming out of the toilet. So that will be sort of sanitary or vent piping that runs to the roof. Now, when you get heavy rain or floods or other items, you'll need somewhere for the water to go. That is what is referred to as stormwater drainage. So that is your roof guttering and roof plumbing and downpipes and connections to some sort of stormwater drainage system that water can flow into. Obviously, that water will then flow typically into waterways, so it needs to be segregated from your sewage and your dirty water. And then finally, on larger commercial buildings or industrial facilities, it will typically have some sort of wet fire protection system, which may have its own pump system, or it may have hydrants that the fire department can connect through, and then some pressurized distribution of that water that flows to sprinklers and so when a fire starts, the sprinklers turn on. Now, the dry fire protection system would be covered more under sort of an electrical or a service scope of work, but really for plumbing, on plumbing quantity takeoffs, we're really interested in these 5 different types of services. And all these services, it's really going to come down to 2 things. It's going to be measuring the lineal meters of pipework and reticulation, and then counting things like the number of sprinklers, the number of stormwater pits, the number of hot water units we have. So it's Plumbing quantity takeoffs are very, very simple once you know what you're actually looking at. Okay, so the next part of the plumbing takeoff is to actually understand the drawings. So we understand roughly what the system is. Now we have to look at the drawings to see how this system is built on our specific project. It's really only a handful of different types of drawings. We have general notes or cover pages within which we will have sort of schedules and explainers of all these different systems. Our schedules, again, might be on the general notes page, might be on separate drawings, will give us almost all of our counts if the drawings do have schedules. So a lot of the time, instead of actually counting how many hot water units you have, you can simply refer to the schedule at the front of it, and you'll be able to see a list of all the different hot water units, for example. Then we have our layout plans. So layout plans are a scaled representation of the building, often done on the architectural layouts, and they simply show where all the different pipes are running, and then we can take our lineal measurements of this. The only thing we would have to be aware of is when there is changes in heights. For example, we have a vent stack going to the roof. We obviously need to factor in that some of these pipes will be rising vertically, so we can't simply measure the lineal meters on a 2D representation of a plan view. So typically the plumbing drawings will have schedules at the front that tell you how many of your fixtures, your fittings you have. Sometimes they won't, and you'll have to count that. But even if they don't tell you, for example, the number of fittings, they might give you references to the drawings or tags. For example, this is WC1 and a description of what that item actually consists of. Or for example, there's a trench drain and then it's got a detailed description of what that trench drain is actually made up of. Then we'll typically have a layout drawing for each of the different types of services. So this is the, what's this? This is the wastewater and vent layout drawing. Then we have a cold water reticulation drawing, which I believe also has, so they're calling this domestic water, but if you look at the legend, the cold water is, oh, I'm scrolling terribly. The cold water is as a thick black line and the hot water pipework is as a dashed black line. So we've got both those services on this one set of plans. We can also, I believe, see where the bathrooms are. You can see the water's running into that. And then we can look at, for example, where the water heaters are. So WH1, WH2, if we go to the schedule. The other way you can do this is just using Control F and searching. So yeah, that's a wall hydrant. So yeah, all the items will be shown with the text tags and then we can reference those. Now, because this is a commercial building for a supermarket, they actually have some layout drawings for condensate drainage, where for example, you have a fridge or some sort of evaporative cooler and it causes a lot of condensation. They've got a separate set of drawings showing how these condensate units, the drip trays, will then go and connect to the plumbing. And they also have a gas. They're also showing, no, sorry, this is the plumbing roofing plan. So this is the stormwater drainage on the roof and how that flows into the downpipes. And then they're also showing a dimension plan which shows the set off to all of the different points. So you could use this to get more accurate measurements. Okay, so those are our layout drawings. The final part of this is, so it's talking about, we've got schedules and general notes. We've got our layout drawings where we can get our lineal meters of pipework. And then at the end, we have section views, which are detailed sort of close-ups or maybe even isometrics, like you can see here, of the exact connection arrangements. Okay, so how are you actually going to use all this information and basically turn this into a full bill of quantities? Well, number one, you need to work out what you need to measure. So for us, this is going to be for the different trades. So cold water, hot water, plumbing, we're going to need both the counts of all the fixtures, fittings, and units that we're installing, and we're going to need the lineal meters of that. And then we're going to then need to work out our assemblies. So an assembly is, if you think of measuring the lineal meters of pipe, is what I refer to as a primary quantity. It's something you physically measure on the drawings, but associated with that primary quantity, we'll have a whole list of items to install that. So for example, per lineal meter of pipe, we might need a hanger, we might need some sealant, we might need fixtures to connect the pipe. So rather than actually and it's impossible to do this. Rather than actually counting how many hangers we need, which would be impossible from the drawings, we take the primary quantity that we measure, which is the linear meters of pipe, and then we derive the number of hangers and other units from that. So that is what is referred to as an assembly. Now, some people within their assemblies will only include materials, but for example, if you're doing an estimate, often it's good to include that your labor within that assembly. So for example, a floor-mounted toilet. For every one we count on the drawings, we also need a cistern, we need a seat and cover, we need a connector with an S-trap collar for the wastewater, we need a flexible water connection for the actual water supply to the toilet, we need a stop valve, we need the floor fixings, we need silicone to seal it, we need 2 meters of pipe, we need 2 meters of a cold water branch, we need pipe fittings, then we need labor to install it. So 1.5 hours for the rough-in, 0.75 for the fit off, and 0.25 to test and commission. So obviously these numbers you could change depending on your specific type of toilet and the labor allowances you want to leave. But what this really means is for every one of these we count on the drawings, these are going to be our secondary quantities that we derive from this. Now, if I was doing the estimate for the project, I would include the labor hours within my assembly. But if I am only doing the bill of materials because I want to order this material, I wouldn't worry about the labor. I'd be much more worried about getting these secondary quantities correct. The tool I'm using to view these set of drawings is just Bluebeam, but I find Bluebeam for quantity takeoffs isn't great. I much prefer, and I'm using a lot now, a tool called ZZ Takeoff. But whether you use ZZ Takeoff, Bluebeam, PlanSwift, whatever, the process is all exactly the same depending on what software you use. So it doesn't really matter what software you actually use, but the principle we're going to follow is we're going to set up an assembly in this. We're going to set up assemblies for all our different items, and then we're going to measure this on the plans, and the software is automatically going to derive our full bill of materials from our primary quantity takeoff. So the first example I'm going to give you is a linear count, which is where we measure the linear meters of pipework. So first we need to set up an assembly for what we're actually going to be measuring. So this is the waste and vent water. So I'm going to create a new linear count. I will auto scale these drawings. Now I'm personally going to struggle with this because these drawings are in imperial and I can't think in imperial, I only think in metric, but let's try. So let's call this takeoff wastewater pipe. And so that is going to be our primary quantity, which is a linear meter measurement of wastewater pipe. So next we have to put in our secondary bill of materials associated with that. So that is going to be DN100 PVC pipe, which is just the linear. We're going to put 5% wastage on that, and we're going to round up to the nearest 3 meters because they come in 3 meters length. And that is going to be in the unit is going to be linear meters. The next one is we're going to need our actual pipe supports or hangers. Let's create this as hangers, and we're going to need a hanger every 3 meters. So it's going to be the linear meters divided by, no, it's probably going to be every 2 meters, isn't it? Rounding up to the nearest one. And again, we won't put any wastage on the hangers, and that is going to be a count unit. So it's going to be the linear meters divided by 2. So 1 hanger every 2 meters. We're going to say we're going to have a connector every, let's say on average 3 meters. So call this pipe connectors. It's going to be every 3 meters. We're going to have 5% wastage on here, and it's going to be round up to the nearest 1. Let's say, and then the install, it's going to be 0.25 man hours per meter. So we need plumber, the linear meters times 0.25 because they could install 4 meters in an hour. We won't put any wastage on that, and this will be in man hours, and to install it, they are also going to need a scissor lift because it's going to be hung in the roof. So we'll create a new equipment, scissor lift. It's going to be the number of meters, and we're going to use the same productivity as the install because, for instance, if you're installing it in 0.25 hours, you also need a scissor lift for 0.25 hours, and that is going to be man hours. So once I've got that set up, I can then simply measure the linear meters of pipe from the drawings. I say linear meters, but oh yep, it's put in an imperial for me. So I simply go through and measure it, and I'll only do this section so it doesn't get boring, but you very quickly get the point of how to do this. But you can see I've got wastewater pipe. I've got 62 meters, which means I need 66 meters because it's rounding up to the closest 3 meter length of PVC pipe. I need 32 hangers, 22 pipe connectors, 15 hours of a plumber, and 15 hours of a scissor lift. Now, for the actual floor traps, I could use a count measurement for this. So I'll create a new count, which is wastewater traps, and I'm going to have a grate. It's just going to be a point count. There's going to be no wastage on that. It's going to be each. I'm going to then have a P trap for below that, which is the S bend below the pipe, so you don't get you get water blocking the odor coming up. So that's just going to be, again, a point count. It's going to be the same count as that. We're going to need 2 linear meters of fittings per, let's say 2 linear meters of, that's probably a bit much, but let's say DNC 100 PVC pipe. Let's allow 5% wastage, and we're going to assume we could use the offcuts of the other pipe, and let's say we need 0.5 meters per floor trap. So that's 0.5 meters additional to what we measure on the lineals. That's going to be linear meters. And we're going to need, let's put in there some silicon to seal it. Silicon, and that is going to be 0.5 by 0.25, and that is going to be, say, tubes of silicon. And the final one is we're going to put on there the labor to install it, and let's just say plumber by 2 hours per floor trap, and that's going to be in man hours. Then for the actual floor traps, I simply count how many there are on the plans. Again, it's super difficult, but it's this concept that when I count 10, it's telling me I need 10 grates, 10 P traps, 5.25 additional linear meters of the pipe. I need 2.5 tubes of silicone and 20 man hours to install. Again, these aren't perfect takeoffs. I'm doing this purely to explain the concept of how to do it. Again, you would have to extend this for the full set of plans and set up your own library of assemblies. So often these assemblies will be very typical from project to project. The only thing worth paying attention to is to look at the schedule, which will tell you the exact bits of information you need to build your assemblies and tailor them to a specific project. For example, a trench drain, you would get, it says it's 12-inch wide, heavy-duty channel, slope, precast polymer concrete trench drain system, sloped at 1% towards the outlet. So that is just, so if you have a standard assembly for a trench drain, which might just say polymer blah, 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 or precast polymer shell, you could just customize it to being 12-inch wide, would be the level of customization you have to do for the project. Or if I show you another example, this is a water closet, and this is a Virtuous China wall-hung siphon jet, 1.5-inch top spud with Sloan Ecos A01. Battery-powered, sensor-operated, auto dual flush valve with polished chrome finish. So that is the information that would go into your assembly. So basically what you work out is for every WC1 water closet, this is the information, or these are the bits of materials that you would use to derive your secondary quantity for that. But again, a lot of the units that you would count, they will often be in the actual schedules themselves. So you don't even have to go and count them all in the drawings. You can simply refer to the items in the schedule to get your counts or your bill of materials for this. Again, takeoffs are super easy if you actually understand what you're looking at. I'm not amazing with plumbing stuff. I have a pretty good understanding of it, but really, if you understand what the drawings are actually showing, that this is wastewater, this is cold water, this is hot water system will have some sort of boiler or heat unit. It'll have hot water piping that's separate to cold water piping. If you sort of understand things in that level of detail, you understand this concept of an assembly and how to set up your assembly specific to a project, then you can very quickly and very simply complete your quantity takeoffs. Here's a step-by-step guide to electrical quantity takeoffs. There's 3 steps to this process I'm going to be covering. Number 1, determining what we actually measure. Then how to measure it, and then finally how to convert your measurements to a full bill of quantities using assemblies. The software I'm going to be doing this in is ZZ Takeoff, but the actual principles behind it are software agnostic. It doesn't matter whether you're using PlanSwift, Bluebeam, or whatever. I just personally think ZZ Takeoff is really easy to use and very intuitive, and I'll also put a link in the video description to a library of the assemblies I'm using to do this takeoff. And the term assembly is going to make a little bit more sense in a second. So as I said, there's going to be 3 steps we go through in this process of doing a takeoff. So number 1 is going to be determining what we actually are going to measure on the drawings. These are the items that we can see, that we can easily count. For example, in this drawing, there is a number of light fittings to measure. We'll be measuring those, or we've got linear meters of cable tray. The second step is going to be the very confusing and complex process of either counting items or measuring lengths. And then the final step in the process is how we take the measurements we've made and then use these to create a full bill of quantities. Because there are some items on the drawings that are not easily measurable. So we use assemblies to derive the quantities or the full bill of materials for those from the primary quantities that we measure. So number 1 is determining what we actually measure. And the rule behind this is basically you measure anything that is visible on the drawings and that isn't already provided in other information. So for example, on the drawings, we can see that there is cable tray shown. So we can measure the linear meters of cable tray. We can count the number of power points and light fittings. But if these were provided in another schedule that the client provided, then we would rely on that bit of information. So we're only really measuring what is easily accessible on the drawings and what isn't already provided. So for electrical, this would typically be your cable containment, your conduits and trunking, the cables if the client isn't already providing a cable schedule, but most of the time they will provide a cable schedule. We've got the lighting quantities, the switchboards and distribution boards, power outlets and accessory, any fire detectors and alarms, any data and communications, and any earthing and lighting protection. Now, there are quantities, and this is where I'm getting into this idea of an assembly. There are some quantities that would be derived from, so I would refer to these as your primary quantities. There are some quantities and bill of material items that you can derive from these. For example, if according to the drawings, every 2 meters we need to have a support for our cable ladder, then we wouldn't actually count the number of supports, or it probably wouldn't be shown on the drawings, but that would fall under our cable ladder assembly. So if I show you an example of an assembly for cable tray, every linear meter of cable tray, so what we're going to measure is the linear meters of cable tray. We have 1 splice plate every 3 meters in length because we're buying the cable tray in 3 meter lengths. We have 1 support bracket or hanger every 2 meters. So we have 0.5 support brackets per meter we measure. We need 0.25 linear meters of threaded rod per linear meter that we measure. So as you can see here, if I go to my drawings and I measure the quantity of cable tray, then that is my primary quantity. And then using an assembly, we derive all of these secondary quantities from. Now, it depends what you're doing your takeoff for. You might only be interested in procurement, so you only want to derive a bill of materials from this, but you may actually want to be doing this for an estimate, so you might also apply productivity rates to these items to calculate your total hours. So for example, if you measure a linear meter of cable tray, that might take an electrician 0.4 hours to install. So from our primary quantity, the length of cable tray, we're deriving our secondary quantity, which is the man hours to install that. Whether you're using this just for your bill of materials or your quantities, again, it depends what the takeoff is for, but this is the idea of an assembly. So we can have assemblies for underground conduits where we're deriving the amount of trenching we need to do, the amount of warning tape, the amount of bedding sand we need, all based on that original trench profile. So if I use the example of a light fitting, the primary quantity that we're going to count on the drawings is the number of these individual light fittings, but from this primary quantity, we can derive that we need 1 suspension chain and hook set. Again, this is for a hanging light. We need a mounting bracket. We need a junction box, 1 per light fitting. we need 2 meters of cable on average per light fitting. We need cable fixing, all these items. So again, the only quantity we're measuring is this. These are going to be pre-built assemblies we set up in our takeoff software that automatically calculate based on the primary quantity we measure. Now, the other really important point to bring up here is because if I'm using this for the purpose of procurement, this isn't as relevant, but if I'm using this for the purpose of estimating and I want to calculate the labor cost per item I install, then the different productivity rates and different plant requirements for different tasks becomes very relevant. So for example, some light fittings you might be able to install from a ladder. Others, you might need an EWP or boom lift to do it. So when you're doing a takeoff, you would need to break down which ones are easily accessible from a ladder and which ones you need a boom lift for. If you're doing this for procurement and for the purpose of buying the light fittings, that doesn't actually matter. But if you're doing it for construction and installation, you have to think about what are all the different productivity rates, what are all the different access requirements, plant requirements that we'd need for these different tasks. So to make this really simple, I'm going to do 2 examples, one of measuring light fittings, the other one for measuring linear meters of cable tray. And again, it's the actual measuring act is the easiest. The bit you really have to think about is how you set up your individual assemblies. So for example, here I have a set of light fittings and I'm going to set up a takeoff item, which is my B2 light fitting. So I'm going to do that. I'll create my first assembly. And obviously if it's light fittings, we're going to be counting them. So first I'm going to call this assembly B2 light fittings. And again, I just want to stress that this is using ZZ Takeoff, but whatever takeoff software you use, the principles are all exactly the same. You have a primary quantity you measure, you have a secondary quantity that you derive things from. So then I'm going to add material, labor, and plant items below this. So number 1 is going to be the actual light fitting itself. So open that up, light fitting, and the ratio is going to be 1:1. So the units are going to be each, and the formula is just going to be point count. The count of my light fittings is going to be the number of items that I count. The next one I'm going to add is, let's call this the support bracket. And again, this is going to be a 1:1 ratio. So the formula is just point count. Again, the same units. But let's say with support brackets, we want to add 5% wastage because it's a consumable item. We may use some up. So then the next one I'll say is material. Let's call this the sub-circuit cabling, or we'll call it 2.5 mil squared electrical cable. We want 10% wastage on cable. We want, that's going to be units, not meters squared. It's going to be linear meters, and it's going to be that times 5 because we want 5 meters of cable per light fittings. We save that. I'm actually going to go back and put costs into each of these. You can use this or you can export it to Excel. It really depends what you want to do. Let's say the support bracket's $25. The light fitting is, say, $365. Again, you can put cost in here or you cannot, or you can just export to Excel. It's whatever you find easiest. Let's say, so we've got the cable, the support. Let's say to then install that, it's going to be 2 man hours per assembly to do that. So electrician units is man hours. So we've set that up. That is now assembly for B2 light fittings. We copy that across to our takeoffs. And then if I go and start counting, these, 1, 2, 3, 4. Again, this is very complicated and very difficult stuff. It's definitely one of the toughest things you will do. I think that's all the B2 light fittings. The rest of these are all B1s. Oh no, there's a few here. And there we go. There is our quantity of 16. And you can see from our primary quantity, for the count of 16, we've got 16 light fittings. Again, makes sense. We've got 16.8 brackets because we've allowed for 5% wastage on the brackets. We've got 88 meters of cable because we've got 5 meters of cable per fitting with 10% wastage, and we've got 32 man hours. So then you can see from this primary quantity, we've automatically derived our secondary quantity. And over time, you can build your own library of all your different takeoff items. So I'll put this spreadsheet as a link in the video description. But again, this is just an example. You might want to change your productivity rates. You might want to change different things. But in all these takeoff softwares, you'll be able to have a complete library of these items. So I want to create another takeoff item, but this one's going to be a linear measure, cable tray, and we're going to have the actual material, which is going to be our cable tray, which we want 10% wastage on. So round up to, this is an example of where you could use rounding up when you do it. I don't like to do that because it depends on the quantity of the job. I think you allow for a little bit of extra fat if you do it like this, but you could round up. Say you buy cable tray in 3 or 6 meter lengths, you could round up to the nearest 3. So your total quantity is going to be, it's always going to come up to the nearest 3 meters, which factors in the length of cable tray. But if you buy them in 6 meter lengths, you'd round up to the nearest 6. But let's just say 3. We've got a cost per unit is meters or linear meters, if you want to do it like that. And our cost is going to be, let's say, $35 per linear meter. Then we'll add, I didn't name that, cable tray. I'll put in electrician, and let's just say that is times 0.4. So our productivity rate is 0.4 per linear meters. We want to allow for a little bit of wastage on the installation. It's going to be, that's our labor to install it. And then we want, call that a material, cable tray brackets. That is going to be linear. We've got a bracket every 2 meters. So if you imagine that, if we want to turn that into a number of brackets, we've got 6 meter cable tray, we need 3 brackets. That's why I'm multiplying by 0.5. Let's just say they're $30 each. And then let's also add the cable tray splice plates. Material, linear meters times 0.3, because we've got 1 every 3 meters, so 0.33. Round up to the nearest 1 each. Let's just say these are $10. And there we go. There we've got our cable tray assembly. We copy this into here. We select it. I didn't scale the drawing, did I? It's auto scaled to 1 in 100. I just double check that that is correct. Yep, the scale is correct at 1 in 100. And let's measure the linear meters of cable tray. Just select that. Oh, no. I clicked too far. Delete that. Oop. Accidentally deleted the takeoff item. I'll copy that back. I'll select. So you see we've measured 24 meters there, which gives us 27 meters of cable tray with the wastage, 10.26 man hours, 12.2 cable brackets, and 9 splice plates. So I'll measure a bit more. Again, any electrical stuff, unless someone can give me like a good, I'm happy if someone tells me that I've like missed something obvious, but it's either counting or measuring stuff. It's actually very, very easy to do. No, I clicked too far. Delete that measurement. And again, like if you're measuring, like if I was doing this drawing and I'm measuring something that's blue, I would change the color of that so it's easier to see. So you might want to change it to red. Oh, actually, there's a lot of red in this. So maybe green. So then it's much easier to see what you've measured. But I mean, these are just little tricks. You're obviously going to learn this by actually playing around and doing one. And there we go. So that's 94 meters. And then that spits out our secondary items. And then we can go to the reports tab and we can see a summary of all our bill of quantities by item, or we could see it by, we could see it grouped by takeoff item, or we can group it by the actual items. So for example, the software's gone and actually combined electrician. So we measured some counting electricians, and then some of the electricians were from linear measurement. So it's combining, if we name the resources all the same way and give them the same units, we can then group it by the item we're counting. And then if you want to, you can just export this to Excel and then build your estimate on that. I mean, it's super simple. If you want the library of some standard assemblies and ways to do it, again, you should customize this to how you do things, your productivity rates. But you can use something like this to set up for your primary quantities your own template library of assemblies. Now, this is just me talking about how to measure stuff, but if you want to actually know how to compile electrical estimates properly, then watch this video next. Here's a step-by-step guide to HVAC quantity takeoffs. Before we measure anything, we first need to actually understand what is on a set of HVAC drawings and how to read and interpret them. Then we need to build our library of different assemblies and then perform our counts and our measurements. And I'll put a link in the video description to a complete library of different HVAC assemblies and a simple Excel template you can use to record your takeoffs. Okay, so first up, these drawings aren't actually going to mean much unless we can understand the different components shown. Now, for some of you who already have a good understanding of HVAC and mechanical works, you can skip ahead. But I think it's important to actually go through the different components of a system, and that'll make sense later on when we talk about what we should actually be measuring and what we can just derive from our primary quantities. So when we talk about mechanical or HVAC, we're really talking about the system that either heats air, cools air, or distributes fresh air throughout the building. So then the actual components of the system will be a centralized unit that either heats or cools, and then ductwork that distributes it, and then we've got diffusers that will distribute that air into the building space. So the first set of items we need to understand are the actual components of the system. So these are the things that generate or cool air, and we have chillers that cool things, we've got boilers that heat things, and we've got cooling towers and air handling units that do a combination of the both. Most large commercial buildings will have large air handling units that both can be used as both heaters and coolers, but some buildings may have specific boilers or chillers as standalone systems. We also have fan coil units, which can be think of as smaller, localized heaters or coolers. This hot or cold air is then distributed through the building through ductwork. So ductwork is simple, it can be rectangular or circular, but it is metal casing that contains the air. And then when the ductwork ties into a building space, we will have either diffusers or grills that act as almost like a vent cover to the ductwork. The other component of the system that is important to understand is the actual building management system. So this is typically referred to as the HVAC electrical system or mechanical electrical system, but this is the comms and controls that tells certain things when to turn off, when to turn on, connects to the meters and the control panels in different rooms, basically runs the entire building system. So this, when we talk about doing a takeoff for a building management system, that would fall under the category of an electrical takeoff. So I'm just going to be talking about the actual core components and counting those, and then deriving the ductwork. Okay, so the basic process of performing a quantity takeoff is step one, you need to determine what you are actually going to be measuring. Now, when we're talking about what we'd measure when we do a mechanical takeoff, really it's going to be counting the core components of the system. So the air handling units, the fan coil units, which will be a count sort of takeoff, and then the lineal measurements of ductwork and condensate pipe. They are our two primary measurements. All of the secondary components of the system, like the number of hangers, fixings, secondary items, we derive from these primary lineal measurements. Okay, so if you're not familiar with the concept of an assembly is basically a ratio of a primary quantity to a secondary quantity. So the primary quantity might be something you count on the drawings, like the number of fan coil units. Our secondary items are all the secondary measurements we derive from the primary quantity. So for example, if we count one fan coil unit, we obviously need one fan coil unit. We need one mounting bracket. We need one ceiling access panel. We need 1.5 meters of duct to connect to this. We need 2 chilled water flexible connections. We need 1 control valve, 1 strainer, and so on and so forth. So basically, what we do here is we have a primary unit, which we're counting, and then all of these secondary items, rather than measuring all of them specifically or counting them all separately, we only have our one primary unit that we count, and all of these secondary items get derived from the primary quantity. Now, some people, when they're doing a quantity takeoff, will only talk about the actual bill of materials, or you might want to derive a full bill of quantities, which also includes your labor and plant. So for example, if you have one fan coil unit, you might need 2.5 man hours of a mechanical fitter to install that. So for every fan coil unit we count, we then have 2.5 hours of labor from a mechanical fitter. We have 1.5 hours of a pipe fitter to connect the piping. We have 0.5 hours of insulation work, and we have 1 hour of electrician to come and connect up the electrical power to it. So it really depends how you want to do it and what your goal of doing the quantity takeoff is. If you're doing a quantity takeoff for procurement, you're obviously not interested in the total number of labor hours. You're much more interested in accurately measuring all of these secondary quantities. But if you want to build a full construction estimate, then yes, you'd want to derive these labor quantities from your primary quantity. But if you're doing a conceptual estimate and it's early on in the project, you might not care about the different types of fan coil units, whether it's ceiling exposed or ceiling recessed, and the minor differences in secondary quantities. So you might group some of these things together. So it's really important to understand the purpose of the takeoff and whether you want something very specific, very detailed, a very detailed bill of materials for procurement, or whether you're just doing a conceptual fast estimate and you're happy to group more things together, whether you want to include labor and plant or this, or whether you're doing this just for materials. Now, the other thing worth noting is most mechanical drawings will include a mechanical schedule, which will be a schedule of the specific items within the scope of the project. They often won't give you the lineal meters of ductwork, but they will give you a count of the number of air handling units, fan coil units, or major bits of plant and equipment. So in that instance, we don't even have to count these items. We can simply go to the schedule and derive them. So for example, this set of drawings gives us the mechanical motor list. I'll just close that so we got more space. It gives us the mechanical motor list. It gives us the number of air handling units. It gives us the number of air conditioning units. It gives us the number of diffusers and grills. It gives us the number of heat recovery ventilators, fans, and so on and so forth. So we don't actually have to go through the drawings to drive these. For all our unit counts and our primary equipment, we can simply use this list. So the other thing you can see is on the actual layout drawings, it is showing all the electrical connections for the building management system, and it is giving references to each of these specific units. So HRV2, if we go back to the mechanical schedule, we go to heat recovery ventilators, HRV2, that is a reference to the heat recovery ventilator. So these layout plans are simply referencing these schedules. Other thing worth noting is that, again, it depends a little bit on the purpose of the takeoff, but if we're talking about condensate pipe, which might be like a couple of dollars a meter, this sort of minor consumable installation, I would not go and do linear measurements of all of these items. I would include that in the assembly for this specific AC unit. Because at the end of the day, whether you're doing this for procurement or whether you're doing this to prepare an estimate, at the same time someone goes and installs this, they'll also install that refrigerant line. So it doesn't really make sense to go get detailed lineal measurements of each of these individual items. Your actual labor, plant, materials is all going to be more or less correct if you simply count or take this number from the schedule rather than actually going a linear measurement for all this. So when we're talking about what to measure, most of these sort of conduit, these small items where you'd have 3 or 4 meters per individual fitting. If we're talking about the actual VMS system and the cabling for that, again, you could just derive that rather than going and actually measuring out exactly how many meters of cable this is. You could just derive that from the number of units. Okay, so once we work out what we need to measure, I'm going to do 2 simple examples. I'm going to do a count item. Again, this is a bit redundant because the quantities are actually given in the schedule, but to prove a point, I'll do a count measurement and I'll do a linear measurement of ductwork. So really, those would be the 2 primary things we'd be measuring. Everything else we would be deriving from our secondary quantities. Okay, for our count item, let's do the number of air handling units. So the first thing we're going to do is we're going to set up our assembly. So to set up an assembly, I'm using ZZ Takeoff, but honestly, like all the takeoff tools are very similar. ZZ Takeoff is just one I like. So we set up a new count, which is, let's call it air handling units. It's a point count. And then the first item will be material, which is the actual AHU itself. Then we will have the, let's call this the flexible ductwork connections. And we're going to have 2 per item. So it'll be the number we count multiplied by 2. Will allow for, again, 6 meters of ductwork, which would be 6 meters of ductwork within that. Will allow for a, let's call that, let's say power cabling. Will allow for 10 meters of power cabling to connect it. It's going to be meters. I should have fixed that. So it's meters. Now, really, obviously, this is going to be very specific to the actual item you're counting. We're going to need, let's add this as a labor. We'll call this mechanical fitter. It's going to be, say, 8 hours. So 2 guys for 4 hours to install. Put that as man hours. And then we're going to need a crane. It's going to be 4 hours to install. Then I can simply go to the drawings and I count all the air handling units if I can find them, which they're going to be on the roof, which is, there's 1, 1, 2, 3, and you can see from my primary quantity, it's told me I need 3 air handling units, 6 flexible duct connections, 18 meters of ductwork, 30 meters of power cabling, 24 man hours of a mechanical fitter to install them, and 12 hours of a crane. Now, again, that was an oversimplistic assembly, but really you could build more complicated assemblies like this where you have 20 secondary quantities derived from a primary quantity. You could make them precisely specific to exactly how you want to measure your quantities. And you could even do some samples. Say you had 20 air handling units, you could go measure 1 or 2 of them and to get the average amount of ductwork per air handling unit and make these more accurate and specific to your project. Okay, the next example I want to do is a linear meter measurement, which is going to be ductwork. So we're going to create a new linear measurement. Let's call that ductwork, but it's ductwork 14 inch by 12 inch. It's going to be a flat linear, but we can also get linear with height if we're doing ceiling transitions. Okay, so I want to create my secondary item. So the primary one is obviously just going to be the same as the length, but it is going to be our actual ductwork. (12 inch), and let's say we can only get it in certain lengths or we want to allow for certain wastage, we can put 5% wastage on that. Units are going to be meters. The next one is we need a hanger every 2 meters. So we want to get, let's call this ductwork hanger. We want the linear meters divided by 2 because we're doing one every 2 meters. And again, we want 5% wastage on our number of hangers. The next one is, let's say, where did that go? You go material, joints. We have a joint every 1.2 meters. So we divide that by 1.2, round up to the nearest 1 because it's going to have to be a unit. Then we want a insulation, and we're going to need 2 meters squared per linear meter. Again, depending on the size of your duct, you obviously want to make these specific. And let's call on insulation 10% wastage. And we also need point for labor. We want mechanical fitter, the linear meters times 0.35, because it's 0.35 man hours per linear meter. And that is going to be man hours. And we also want a EWP, which again is going to match the labor productivity. And that is going to be hours. We can start the takeoff and then we simply, again, very complicated, we just measure the lengths of that specific type of ductwork. Is there any other? Just these sections. And that is larger ductwork. So it'd be a separate measurement. For the actual number of diffusers and the building penetrations, we could do a count measurement for that. And again, that's pretty much it. Work out what you need to measure, build your library of assemblies, and then either you count the items or just derive them from the schedule and get your linear measurements of ductwork and derive all your secondary quantities. Very simple, very straightforward. It's not rocket science. It's just understanding this principle of having your primary and your secondary quantities.